Hello, and welcome to Space Historians, where curiosity takes its time and science speaks softly enough for dreams to hear. Tonight, we're venturing into a question that hums beneath every launch countdown, every glimpse of a night sky, and every heartbeat that has ever wondered what lies beyond. How fast can we truly travel in space right now? It's a question that sounds simple, almost mechanical, but behind it hides the story of movement itself, of how we measure speed when the road disappears, and what it means to move through something so vast that motion begins to lose its meaning. Before we start drifting too far, where are you listening from tonight? Maybe you're curled up somewhere quiet, perhaps in a city washed in the hum of late lights, or somewhere rural where the night sky is generous with stars. Wherever you are, there's a kind of motion around you already. The Earth beneath you is spinning at nearly 1,000 miles per hour. That same Earth is also circling the Sun at over 67,000 miles per hour. The Sun itself is orbiting the center of our galaxy at 500,000 miles per hour. You are, right now, one of the fastest travelers in the cosmos without moving a single muscle. That's the first quiet truth of space travel. Even when we think we're standing still, we're hurtling through the void at staggering speed. We live in motion, but we rarely feel it. Gravity holds us close. The air moves with us, and everything nearby shares the same invisible ride. If you find calm in these thoughts, if the gentle collision of science and stillness helps you drift, dream, or simply slow down, I'd be deeply grateful if you'd like this video, and maybe subscribe. It helps this space stay alive, a quiet place for wonder and rest. Now, let's take a slow breath together and begin our journey. Imagine looking up at the stars, not as distant points, but as destinations. We'll explore the difference between the numbers and the sensation. Astronauts often say that once you're in orbit, it doesn't feel like motion at all. You're moving at 17,500 miles per hour, yet it feels like floating. The faster we go, the less we feel it. The human mind was not built to grasp cosmic distances or cosmic speed. We can picture the length of a football field, the span of a mountain, perhaps even the curve of the planet from space, now that we have seen the photographs. But numbers like light years, or millions of miles per hour, slip through the fingers of our intuition. Tonight, we are not going to rush. We will take this one layer at a time, as if stepping gently through the gears of the universe. Speed, in its simplest form, is a relationship between distance and time. It is how far something moves, and how long it takes to get there. Here on Earth, that idea is almost comforting. We understand the speed of cars, trains, and planes. We can measure their speed against a map, feel it in the rumble beneath our feet, or see it in the blur of passing scenery. We have context. We have resistance. We feel the air pushing against us. We hear the sound of our own motion, and we feel the solid ground resisting the push of our engines. But in space, that context vanishes. There is no wind, no sound, no passing scenery to offer a reference. There is only emptiness and acceleration. In the vacuum, there is no air to resist, no friction to overcome. This is the impossible beginning of our story, the profound and deeply human contradiction between the reality of our motion and the feeling of our senses. The hook is this: even when you believe you are perfectly still, you are already moving at speeds that defy imagination. Think of the ground beneath you. It feels solid, fixed, the very definition of stillness. Yet, if you are near the equator, that ground is moving eastward at about 1,670 kilometers per hour, or nearly 1,000 miles per hour. You don't feel it, because everything around you shares that same motion. The oceans, the air, the trees, the buildings, and the chair beneath you are all moving together in a single, perfectly smooth system. It is like being in a train car with no windows, moving at a perfectly steady speed. You would never know you were in motion. That spin, which gives us the rhythm of day and night, is just the first layer. The entire Earth, our whole world, is also orbiting the Sun at about 30 kilometers per second. That is over 67,000 miles per hour. And still, you feel nothing. But the Sun itself is not stationary. Our entire solar system, carrying the Earth with it, is sweeping around the center of the Milky Way galaxy at a staggering 220 kilometers per second. That is 500,000 miles per hour. And the galaxy, in turn, is gliding through the universe at even higher speeds. You are, right now, as you listen, one of the fastest travelers in the cosmos, without moving a single muscle. This is the first quiet truth of space travel. Even when we think we are standing still, we are hurtling through the void at staggering speed. We live in motion, but we rarely feel it. We cannot. Our human perception is not designed to sense velocity or steady speed. We can only sense acceleration, the change in speed. The steady cosmic motion of our planet passes utterly unnoticed. This is where our story truly begins. Because to travel in space, we must first change our speed. We must accelerate. And that is a feeling we understand all too well. Every rocket you have ever seen on a launch pad is a vessel designed for this single purpose, to accelerate. It is a tower of stored potential, filled with propellants, a fuel and an oxidizer, waiting to meet in a combustion chamber. Because space offers no oxygen to burn, the rocket must carry its own. This adds mass, which means it needs more fuel to push that mass, and so on, in a delicate, towering compromise. When the engines ignite, the feeling is the exact opposite of the stillness we just explored. It is violence, it is fire, it is sound. Thousands of kilograms of propellant are consumed every second. The sound becomes a physical force, a thunder that shakes the ground for miles. The pressure and heat are immense. For the people inside, the push feels like a giant hand, pressing them into their seats with forces of 3 or 4 times Earth's gravity. Breathing becomes heavy. The vehicle shakes, flexes, and groans as it fights the atmosphere. This is motion as we know it, loud, powerful, and demanding. And then, in an instant, it stops. After only a few minutes, the engines cut off. The silence is sudden, absolute, and eerie. The relentless pressure vanishes. The weight disappears. Everything that was heavy is suddenly light. And for the first time, the Earth looks like a sphere, a curved planet glowing blue beneath a black sky. This is the impossible beginning. The astronauts are now moving at 17,500 miles per hour, or about 5 miles per second. They are traveling 27 times the speed of sound. They will circle the entire planet in about 90 minutes, passing from daylight to darkness 16 times a day. And yet, it feels like floating. It feels like stillness. Inside the cabin, there is no sensation of rushing. Coffee floats, pens drift, hair curls slowly in the air. The astronauts, who are now the fastest humans alive, feel no motion at all. Their sense of speed is purely visual, not physical. They watch continents glide past below, oceans fade into the horizon. But inside, the world is calm. This is the central hook of our story. This is the strange, beautiful, and deeply contradictory poetry of space travel. The faster we go, the less we feel it. The more energy we burn, the quieter the universe seems to become. This experience forces us to ask a new question. What does fast even mean in a place with no reference frame? On Earth, we measure speed with experience, In space, we measure it with math. The question of how fast becomes as philosophical as it is physical. We are really asking how far we have come in mastering movement through nothingness. To achieve this mastery, we must first pay a steep toll. Nature charges this toll for leaving home. To rise above the atmosphere, you must overcome the grip of gravity, and that means reaching a precise number, escape velocity. For our planet, that speed is about 11.2 kilometers per second, or about 25,000 miles per hour. This is not the speed to orbit, but the speed to break free entirely. If you could hurl a stone at that speed, it would never come back down. It would slip forever into the deep. Every mission that has ever left Earth's orbit, from the Apollo journeys to the Moon to the robotic probes heading for distant planets, has had to pay this price. And this is where we meet the first great challenge of space travel. Rockets, the fiery engines of our acceleration, are constrained by a merciless truth. It is called the tyranny of the rocket equation, a formula that governs the relationship between velocity, fuel, and mass. The equation, in its simplest form, says this: to go faster, you must expel mass. But to do that, you must carry that mass with you as fuel. This fuel adds weight. This weight, in turn, requires more fuel just to lift it. The cycle is exponential. This is why a rocket on the launch pad is so disproportionate. It is a thin needle of payload, the capsule or satellite, sitting on top of a mountain of fuel. Less than 10% of its weight at launch is the thing it is actually meant to carry. Everything else exists only to disappear. This is the price of acceleration. It is paid in fire, in mass, and in energy. The roaring flame of a rocket lasts only a few minutes, but what it achieves is a momentum that can last for years, or even eternity. Once the engines shut off, the spacecraft does not slow down. In the vacuum, without air to resist it, motion is eternal. Every object that has ever left Earth is still moving. The probes, the satellites, the discarded stages of rockets, all of them are still coasting, silent and steady, on their endless trajectories. This persistence is both beautiful and unsettling. On Earth, friction is a guarantee. Things stop. In space, inertia is the guarantee. Things do not stop. This is the impossible beginning. We live on a planet that feels still but is moving at incredible speed. To leave it, we must create a moment of profound violence and acceleration. But the moment we achieve that speed, the moment we pay that price, all feeling of motion vanishes. We are left in a state of perfect, silent, weightless calm, moving faster than any human has ever moved before, and feeling nothing at all. This is the paradox, and it is from this strange, quiet stillness, this floating peace at 17,000 miles per hour, that our journey truly begins. Our story of speed begins, as all human stories do, right here, on Earth. It begins not in the sterile vacuum of space, but in the thick, resistant medium of our own atmosphere, and in the unyielding grip of our planet's gravity. For thousands of years, we were a species defined by these limits. The sky was not a place to visit. It was an unreachable ceiling, a distant painted boundary where the clouds drifted and the stars watched silently. Our setting was the ground, and our fastest motions were tied to the rhythms of muscle, wind, and water. Humanity has always chased speed, from the first runners who tested their breath against distance, to the first sailors who learned to harness the wind, to the first pilots who broke the sound barrier. Each leap in velocity has changed how we see the world. But these speeds were always, in a way, small. They were movements within our world, not away from it. We measured them in footsteps, in the flicker of passing scenery, or in the whisper of airliners drawing white lines in the upper sky. The setting for our great leap was not one of calm curiosity. It was a setting of tension, rivalry, and fear. The story of how we learned to travel fast in space was born in the mid-20th century, during the height of the Cold War. Two nations, the United States and the Soviet Union, watched each other with suspicion and ambition, and science became intertwined with politics. The sky was no longer just a ceiling. It was the ultimate high ground, a new frontier for a very old contest. It all began with a sound. In October of 1957, the Soviet Union launched Sputnik 1. The world changed in a single, repeating beep. That simple radio signal, transmitted from a metal sphere barely the size of a beach ball, circled the Earth every 96 minutes. Its message was minimal, just a rhythmic pulse, but its meaning was monumental. The sound told everyone on Earth that the sky was no longer empty or unreachable. That little satellite was moving at almost 18,000 miles per hour, faster than anything humans had ever built or sustained. It proved that the Soviet Union could launch something powerful enough to orbit the Earth, and if they could launch a satellite, they could, in theory, launch anything. The race beyond the sky had begun. This was the new setting. It was a race, and every milestone became a contest. The first animal in orbit, the first human, the first woman. In April of 1961, Yuri Gagarin climbed into a tiny capsule called Vostok 1. Atop a trembling rocket, he waited as thousands of tons of propellant ignited below him. The engines lifted him through the layers of atmosphere, past the point where blue turns to black, and into orbit. He completed one full circuit of Earth in just under 2 hours, travelling at nearly 8 kilometers per second. When he returned, his words carried a resonance that outlasted any political speech. "I see Earth. It is so beautiful." It was not just a Soviet victory, it was a human one. A person had circled the planet, seen the curve of the horizon, and returned alive. The race was on. Alan Shepard, John Glenn, Valentina Tereshkova, each flight pushed the technology and the human body to its very edge. The speeds they reached were astonishing, nearly 28,000 kilometers per hour for orbital flight. But what truly mattered was the realization that humans could master this speed. We had entered an environment where speed was not a luxury, but a necessity. In orbit, if you go too slow, you fall back to Earth. If you go too fast, you drift away forever. The race was not just about who could build the fastest machine. It was about who could learn to live in perfect, sustained balance with motion itself. This race, born from rivalry, soon ignited something else. A collective sense of wonder. When President John F. Kennedy declared in 1961 that America would land a man on the moon before the decade was out, it sounded impossible, but it gave the pursuit of speed a new, grander purpose. It was no longer just about beating an opponent. It was about proving that humans could leave their home planet entirely. This was the setting that gave birth to the Apollo program, and with it, the most powerful machines ever built. The Saturn V rocket was a monument to this ambition. It stood taller than a 30-story building and weighed over 3,000 tons. At liftoff, it produced 7.6 million pounds of thrust. When it launched, the ground shook for miles. It was, as some described, a controlled explosion, a harnessed earthquake. Each stage fired in sequence, adding more and more speed until the tiny capsule at its peak reached over 11 kilometers per second, fast enough to escape Earth's gravity. The astronauts who rode these rockets became, and remain, the fastest humans in history. During their re-entry, as they fell back toward Earth, their capsules reached speeds exceeding 39,000 kilometers per hour. That speed was not an abstraction. It was a physical, terrifying reality. As they slammed into the atmosphere, the air in front of their heat shields compressed, glowing like molten metal. The friction was so intense that the temperature outside exceeded that of the surface of the sun, and yet the crew inside, protected by that shield, felt only vibration and the steady, heavy pull of deceleration. In July of 1969, when Apollo 11 touched down on the moon, the race that had begun with a beeping sphere reached its quiet conclusion. Neil Armstrong and Buzz Aldrin stepped onto another world, moving slowly in the low gravity. The contrast was poetic. After years of chasing velocity, humanity's greatest achievement in speed ended in a moment of stillness, in a footprint pressed into dust that had never known motion. That moment reshaped our setting forever. The sight of Earth, hanging in the blackness, small, delicate and luminous, changed everything. The astronauts described it as a revelation. From that distance, there were no borders, no rival nations, just one world suspended in darkness. The true destination, they realized, was not the moon. It was understanding our own place in the cosmos. After Apollo, the intensity of the race slowed. The political urgency faded, but the momentum of discovery continued. The focus shifted from raw speed to endurance, from how fast we could go to how long we could stay. The setting became the era of the space shuttle, which turned spaceflight from a one-way mission into something reusable and almost routine. The shuttles orbited at about 28,000 kilometers per hour, delivering satellites, building the International Space Station, and teaching us how to live and work in microgravity. And it was here, in this new setting of long-term presence, that robotic explorers carried the torch of acceleration. Probes like Pioneer, Voyager, and later New Horizons achieved speeds no crewed craft could match. They were light, durable, and tireless. Voyager 1, launched in 1977, used the gravitational pull of giant planets to slingshot itself toward the outer reaches of the solar system. By borrowing momentum from planets, it eventually reached over 17 kilometers per second relative to the Sun. It has now crossed into interstellar space, still whispering data back to Earth across billions of kilometers. Then is our setting. It is a story that begins on a planet where motion is defined by resistance and sound. It is propelled by a human race for dominance, a race that gives us the technology to harness fire and break the bonds of gravity. This race matures into a shared moment of awe, a realization that our planet is a single, fragile home. And finally, it settles into a new, quieter phase of endurance, where patient machines, built by human hands, drift silently on trajectories that will outlast their creators, carrying our first, tentative steps into the stillness between the stars. The journey into space, the quest for speed, begins not with an engine, but with a discovery. It is the discovery of a number, a precise and unforgiving barrier drawn by gravity itself. For all of human history, we lived under a simple rule: what goes up must come down. But in the late 19th and early 20th centuries, thinkers began to calculate the true nature of our planet's pull. They discovered that this rule was not absolute, it was conditional. They discovered the concept of escape. This is the mystery that sparks our entire narrative. To escape is not just an emotional term. In physics, it means something precise. It means reaching a velocity where gravity's pull can no longer call you back. For a planet as massive as ours, a world that weighs 6 sextillion tons, that pull is immense. Gravity is both our protector and our warden. It holds our atmosphere close, it keeps our oceans in place, and it ensures the moon never drifts away. But it also makes leaving expensive. Every gram of matter lifted from Earth must fight against the pull of the entire planet. The discovery was the number that defined the cost of freedom. That number is 11.2 kilometers per second. In more familiar terms, it is about 25,000 miles per hour. If you could throw a ball that fast, straight up, it would never return. It would climb until the air was gone, until the blue faded into black, and it would keep going, slipping forever from Earth's grasp, never falling home again. This number, escape velocity, was the first great discovery. It was the moment we realized our cradle had a lock, and that mathematics had just handed us the key. But this discovery came with a second, more subtle one. What about the speeds below that? This led to the discovery of what orbit truly is. When you orbit the Earth, you are not floating above gravity. You are, in fact, in a constant state of freefall. The International Space Station, for example, is constantly falling toward Earth, but it is also moving sideways at about 7.7 kilometers per second, or 17,500 miles per hour. It moves so fast horizontally that as it falls, the planet's surface curves away beneath it at the exact same rate. The result is a perfect balance, a continuous fall that never reaches the ground. This was the discovery. Orbit is not the absence of gravity, but the mastery of falling. These discoveries were, for a long time, purely theoretical. They existed in the mind of a quiet Russian schoolteacher named Konstantin Tsiolkovsky. In the late 19th century, long before the first airplane flew, Tsiolkovsky was working out the mathematics of reaching orbit. He was the first to truly discover the central problem. He realized that to achieve these immense speeds, you couldn't just build a big cannon. You needed a rocket, a machine that creates motion by throwing mass in one direction so it can move in the other. And in doing so, Tsiolkovsky discovered the great paradox that would haunt engineers for a century. He wrote the formula that would come to be known as the tyranny of the rocket equation. The equation is simple, but its consequences are merciless. It showed that to achieve the high speeds needed for spaceflight, a rocket would need to carry an enormous amount of fuel. But that fuel has mass, and to accelerate that mass, you need even more fuel. To double your final speed, you need far, far more than double the propellant. This was the great, seemingly unsolvable mystery. Tsiolkovsky's own calculations showed that a single-stage rocket, trying to reach orbit, would need to be over 95% fuel, leaving almost no room for the rocket itself, let alone a payload. His discovery was a door that opened onto a solid brick wall. The solution, which Tsiolkovsky also discovered, was as elegant as the problem was brutal. Staging. You did not need to carry the fuel for the entire journey the entire time. You could build a rocket in layers. The first, largest stage would fire, lifting the entire vehicle through the thickest part of the atmosphere. Then, its fuel spent, it would fall away, shedding thousands of tons of dead weight. A smaller, lighter second stage would then ignite, pushing the now lighter craft even faster. By the time the final stage finished its work, only the tiny payload would be left, gliding at orbital velocity. This was the discovery of how to cheat the equation. You didn't just build a rocket, you built 3 rockets stacked on top of each other, each one passing the torch to the next. For decades, these discoveries remained on paper. They were the dreams of theorists. The first liquid-fueled rocket, launched in 1926 by Robert Goddard, was a tiny, fragile device, but it was the physical embodiment of Tsiolkovsky's dream. It was the first small step, the true, undeniable discovery, the one the whole world could hear, came in 1957. When the Soviet Union launched Sputnik 1, it was not just a political statement. It was the final, physical proof of Tsiolkovsky's and Goddard's work. The simple, beeping signal, broadcast from a sphere orbiting at 18,000 miles per hour, was the sound of escape velocity being mastered. It was the sound of humanity discovering that the barrier was real, and that it was, in fact, breakable. Only 4 years later, that discovery became human. Yuri Gagarin's flight in Vostok 1 was the discovery of a new kind of human experience. For 108 minutes, he lived in that state of perfect, balanced falling. He was the first person to experience the profound, life-altering transition from the crushing force of launch to the absolute silent stillness of orbit. This was perhaps the most personal discovery of all. When the engines cut off, the noise and vibration vanish. The pressure that pins you to your seat is gone. Everything floats. The human body, evolved for a lifetime under the constant pull of weight, suddenly finds itself free. The inner ear, which tells us up from down, becomes useless. The heart shifts slightly in the chest. Astronauts describe this moment as a profound disorientation, a disadjustment that the brain must learn to accept. Gagarin discovered what it meant to see the Earth not as a landscape, but as a sphere. "I see Earth," he said. "It is so beautiful." This was the human discovery, that to leave the cradle is not to abandon it, but to finally see it clearly for the first time. The final part of this discovery was one of incredible precision. The journey to the moon, undertaken by the Apollo missions, was not a matter of just pointing and firing a powerful engine. It was a discovery of celestial mechanics, a controlled fall from one gravity well into another. You had to time your launch to intersect with a moving target hundreds of thousands of kilometers away. At the midpoint of that journey, astronauts found themselves in a place called the Translunar Coast, a vast, empty stretch where Earth's gravity was no longer dominant and the moon's pull had not yet captured them. In that space, motion was pure, coasting on the momentum earned from that initial fiery launch. The discovery, in essence, was that space travel is not about force, it is about balance. It is about finding the perfect, steady rhythm between descent and motion, between the pull of one world and the next. It is a quiet, mathematical art, a choreography of trajectories. The roar of the rocket lasts only minutes. The rest of the journey, the part that truly defines space travel, is a long, silent and precise dance with gravity. The discovery that we could leave, that orbit was a balance and escape was a number, did not arrive in a quiet library. It arrived with a sound. The first human response to the reality of space travel was not quiet contemplation. It was shock. In October of 1957, the sound was a simple, repeating beep broadcast from a small metal sphere. The launch of Sputnik, won by the Soviet Union, was a profound, world-changing moment. That simple, rhythmic pulse, circling the globe every 96 minutes, told everyone on Earth that the sky was no longer empty. The realization rippled through the world like a shockwave. This was not a theoretical calculation anymore. It was a machine, moving at 18,000 miles per hour, passing invisibly overhead. The first human response was disbelief, followed quickly by a deep, new, and unsettling awe. This awe was tinged with fear. The Cold War was at its height, and the race beyond the sky had begun. Speed had suddenly become a symbol of power and, perhaps, of survival. The human response was to compete. The milestones became a contest. The first animal in orbit, the first probes to the moon. But the response that truly changed our perception, that shifted the feeling from the shock of a machine to the awe of a person, came in 1961. When Yuri Gagarin orbited the Earth, humanity's response became personal. He was the first human to experience the transition, the first to ride the controlled fire and enter the silent, balanced fall of orbit. And his words, broadcast back to a world holding its breath, became the defining response of our species. He did not speak of politics or of victory. He said, simply, "I see Earth. It is so beautiful." In that moment, the human response became one of profound, collective wonder. We had done it. A human being had circled the planet, seen the curve of the horizon, and returned alive. This was the first and most powerful human response, a sense of shared, fragile, and astonishing achievement. But there was another response, one that was not broadcast to the world, but was felt in the very bones of the travellers. This was the physical human response. This was the feeling of disbelief, the body's own confusion as it was subjected to forces it was never designed to endure. The human body is built for 1G, the gentle, constant pull of Earth's gravity. The response to a rocket launch is one of overwhelming, brutal pressure. The astronauts who rode those first capsules were not just pilots. They were test subjects, enduring a physical trial. During launch, as the rocket fought the atmosphere, they experienced acceleration forces of 3, 4, or even more times Earth's gravity. This was not a gentle push. It felt like weight. Breathing became heavy. Muscles tightened. The body was being pinned into its seat by its own accelerating mass. The rocket itself was responding too. As it climbed, it reached a point of maximum aerodynamic stress, a moment engineers call max Q. This is where the combination of the rocket's speed and the air's density exerts the greatest possible load on its structure. The vehicle would shake, flex, and groan. Every panel, every bolt, every seal was stressed to its absolute limit. The human response inside that shaking metal tube was one of pure faith in the engineering, and faith that the machine would hold together. And then, in an instant, the violence would stop. The engines would cut off. The response to this moment was, perhaps, the most disorienting of all. It was not a gentle release. It was a sudden, shocking, and absolute silence. The crushing weight vanished. The thunder of the engines was gone, and the human body, for the first time in its evolutionary history, was weightless. This was the response of confusion. The inner ear, which uses tiny floating stones to sense gravity and tell the brain which way is down, suddenly had no answer. It became useless. Astronauts described a profound disorientation. The body could not tell up from down. The heart, no longer fighting gravity, shifted slightly. Blood, normally pulled toward the feet, rushed to the head. The body, in its confusion, had to adapt. It had to create a new down, a new sense of here, based only on what the eyes could see. This was the human body's response, an immediate, instinctive, and deeply physical adaptation to an environment that was, by all evolutionary standards, impossible. There was a third human response happening on the ground. It was the intellectual response, the sheer, staggering scale of the effort. The awe we felt watching a launch was matched by the disbelief of the engineers, who knew what it took to make it happen. This was the human response of precision. The price of acceleration was a concept that had to be paid in energy and mass. The Saturn V rocket, the machine that took humans to the moon, was a 3,000-ton vehicle that stood taller than a 30-story building. But the most unbelievable fact about it was that it was essentially a flying fuel tank. Less than 10% of its weight was the payload. Everything else was propellant. In its first stage, the Saturn V burned through 20 tons of fuel every second. In the 2.5 minutes it took to lift the mission to the edge of the atmosphere, it consumed over 2,000 tons of propellant. The energy released could power a city for hours. Here, it was spent in minutes, just to cover the first few hundred kilometers of the climb. The human response to this challenge was to build armies of engineers and mathematicians. It was to invent guidance systems of unprecedented accuracy, using computers that filled entire rooms but had less memory than a modern greeting card. Every launch was an act of collective faith. Faith that the mathematics was correct. Faith that the thousands of components, each one a potential point of failure, would work in perfect harmony. Every trajectory had to be calculated to within fractions of a degree. A tiny error in velocity, a burn that lasted a second too long or a second too short, could mean the difference between reaching the moon and failing, or between a safe return and a fatal one. Finally, there was the ultimate human response. It was the response to the return. The fastest humans in history were the Apollo astronauts, falling back from the moon. Their capsule, pulled by Earth's gravity, reached speeds of nearly 39,000 kilometers per hour. Their return was a trial by fire, in the most literal sense. As they slammed into the atmosphere, the air in front of their heat shields compressed and glowed, reaching temperatures hotter than the surface of the sun. The human response, inside, was to trust the shield, to lie back and endure the vibration and the steady, crushing pull of deceleration, a force that felt like gravity itself returning, a giant hand welcoming them home. But the most profound response, the one that lingers in our collective memory, was not one of fear, or mathematics, or physical endurance. It was one of perspective. When the Apollo astronauts stood on the moon, the race for speed was over. It ended in a moment of quiet, graceful stillness. And when they looked back, they saw it. Earth. Not as a map, not as a collection of rival nations, but as a small, delicate, luminous sphere hanging in the absolute, silent blackness. They saw a single world, suspended in darkness, with no visible borders. This was the final human response. The race, which had begun in rivalry, had delivered an unexpected and transcendent gift. A moment of shared awe, a new understanding of our own fragility, and a new definition of home. The quest for speed, in the end, did not just teach us how to leave, it taught us, for the first time, how to see. We have accepted the impossible. We have seen that we live in a state of constant high-speed motion, yet we feel nothing. We have learned that to leave our planet, we must achieve a precise, violent, and overwhelming acceleration, only to arrive in a state of perfect, silent, weightless calm. These are the paradoxes of the human senses, the difference between what we feel and what we know. But now, we must face a deeper, more fundamental contradiction. This is not a paradox of feeling. It is a paradox of physics. It is the single, stubborn, and merciless law that stands between us and the true dream of travelling through space. It is a law that seems, at first, to make our ambitions impossible. This is the story of the tyranny of the rocket equation. The mystery is this. When we want to make a car go faster, we give it a more powerful engine and a larger fuel tank. But in space, that logic fails. The equation, first worked out by the visionary scientist Konstantin Tsiolkovsky long before we ever reached orbit, reveals a cruel truth. To go faster, you must burn more fuel, but that fuel has mass, and to push that mass, you need even more fuel. It is a cycle of diminishing returns. Each extra increment of speed demands exponentially more fuel than the one before it. This is the tyranny. To understand this contradiction, we must look at a rocket, not as a sleek vessel, but as a tower of stored potential. When a rocket stands on the launch pad, it is a delicate, towering compromise. Look at the magnificent Saturn V, the machine that took us to the moon. It was taller than a 30-story building, but it was not a ship. It was almost entirely a fuel tank. This is the science that defies our intuition. Less than 10% of that rocket's entire weight was the payload. Less than 10% was the command module, the lunar lander, the computers, and the human beings inside. Everything else, all 90% of that 3,000-ton structure, existed only to disappear. It was a mountain of fuel designed to lift a thin needle of payload. The contradiction is that a rocket is a machine built to throw itself away. It works on a simple principle, Newton's third law. For every action, an equal and opposite reaction. A rocket moves forward by throwing mass backward at incredibly high speed. On Earth, engines can be efficient. A jet engine, for example, takes in air from the atmosphere, heats it, and throws it out the back. It only has to carry its fuel, not its oxidizer. But space offers nothing to burn with. Space is a vacuum. A rocket must carry not only its own fuel, but its own oxygen, usually in a liquid, supercooled form. This means more mass, which means more fuel to push that mass. And so, the cycle continues. This is the paradox. The very thing you need to go fast propellant is also the thing that makes you heavy. And the heavier you are, the harder it is to accelerate. Tsiolkovsky's equation showed that a single-stage rocket trying to reach orbit would be an impossibility. It would be a mathematical failure. And yet, we did it. We flew. We reached orbit. We went to the moon. The mystery, then, is how did we solve this impossible problem? We solved it with an idea as elegant as the problem was brutal: staging. If the tyranny of the equation is that you are forced to carry the weight of fuel you haven't used yet, and the even heavier weight of the empty tanks you have used, the solution is simple: throw the empty tanks away. A rocket like the Saturn V was not one rocket. It was in essence 3 rockets stacked on top of each other, each one built to solve one part of the equation. The first stage was the monster. It contained the vast majority of the fuel, its only job to lift the entire heavy structure through the thickest part of the atmosphere and away from the strongest pull of gravity. It would fire for only 2.5 minutes. In that time, it would consume over 2,000 tons of propellant. Then, its job done, it would detach and fall away, tumbling back to Earth, shedding thousands of tons of dead weight. In that moment of separation, the astronauts would feel a sudden, jarring silence. The thunderous roar would stop. They would be weightless for just a second, and then the second stage engine would ignite. A new, powerful thrust would pin them back into their seats. This new rocket, much lighter and smaller, was now pushing only the remaining, much lighter craft. It would burn for several more minutes, adding more and more speed, until it, too, had spent its fuel and was cast away. Finally, the tiny third stage would ignite, firing for just long enough to push the payload into its final, perfect orbital velocity. Staging was the discovery of how to break the tyranny. It was a machine designed to consume itself, to shed its own skin as it climbed, becoming lighter and faster with each layer it abandoned. But this solution, this act of shedding weight, revealed another contradiction. The rocket was fighting not only gravity, but also the air itself. As it climbed, accelerating faster and faster, it encountered a moment of maximum stress. Engineers call it max Q. It is the point where the combination of the rocket's velocity and the density of the air exerts the greatest possible mechanical load on the structure. The vehicle shakes, flexes, and groans under the strain. It is a moment of profound tension. The rocket's own power is threatening to tear it apart. The mystery is that these thin, fuel-filled structures could survive at all. And this leads us to the deepest contradiction, the one that defines the limits of our story. We solved the problem of getting to space, but the tool we used, the chemical rocket, is, in the grand scheme of the cosmos, an incredibly limited, and inefficient engine. The power of a rocket is defined not just by how much mass it throws, but by how fast it can throw it. This is its exhaust velocity. Chemical fuels, whether they are kerosene or liquid hydrogen, are limited by the energy stored in their chemical bonds. No matter how perfectly you design the engine, you can only get so much energy, so much exhaust velocity from burning hydrogen and oxygen. This is the great contradiction of our time. The only engine powerful enough to lift us off the Earth is not powerful enough to take us to the stars. The chemical rocket is a master of the sprint. It gives us an enormous, violent, and brief burst of acceleration. It is the only thing we have that can overcome Earth's gravity well. But it is a terrible engine for a marathon. Its fuel efficiency is, by cosmic standards, abysmal. Once its few minutes of burn are over, the spacecraft can only coast. It will drift on the momentum it was given at the beginning of its journey, a silent, unpowered projectile. This is the science that confronts the mystery of our dreams. We dream of interstellar travel. We dream of crossing the vast distances between the stars. But our most powerful engine is fundamentally incapable of taking us there in a human lifetime. The Voyager probes, the fastest objects we have sent on a one-way trip, are travelling at 17 kilometers per second. Even at that staggering speed, it will take them over 70,000 years to reach the nearest neighbouring star. The contradiction is this. We built a machine of fire and thunder to escape the pull of our planet. That machine, in its violence, gives us just enough speed to enter a state of perfect, silent, eternal motion. But that motion, so fast by human standards, is by cosmic standards a glacial crawl. The rocket solved the first mystery how to leave, but in doing so, it presented us with a new one. How do we go faster, now that the brute force of chemistry has reached its absolute limit? The contradiction was set. The chemical rocket, our great and fiery chariot, had taken us from the ground to the heavens, but it had also shown us its limits. It was a machine of brute force, a sprinter, a master of the first violent step. But the cosmos, we learned, is not a sprint. It is a marathon of unimaginable length. The tyranny of the rocket equation had drawn a line, showing us that with chemistry alone, the journey to even the nearest star would take longer than all of human history. Our ambition had met a wall, and so a new investigation began. This was the moment curiosity turned into quiet, patient, and methodical action. If brute force was not the answer, then perhaps elegance was. If we could not fight the universe, perhaps we could collaborate with it. The investigation split, no longer focused on just bigger explosions, but on new and clever ways to find momentum. The first great answer did not come from a new engine at all. It came from a new way of thinking about the map. It came from the quiet genius of mathematics. We began to investigate gravity itself, not as an enemy to be overcome, but as a potential partner, an engine we could borrow. This was the discovery of the gravity assist. The principle is one of the most elegant in all of celestial mechanics. A massive planet, like Jupiter or Saturn, is not just a destination, it is a moving reservoir of immense orbital energy. As it swings around the sun, it carries a momentum that dwarfs anything a human-made object could ever achieve. A gravity assist is, in essence, a way to steal a tiny, imperceptible fraction of that energy. The investigation became a mission of perfect timing. The spacecraft is launched from Earth, not on a direct path, but on a long, looping trajectory designed to intercept a giant planet. The spacecraft then falls toward this planet, pulled in by its immense gravity well. As it falls, it gains speed, just as a roller coaster does on a steep drop. It then swings around the back of the planet, in the same direction the planet is orbiting, and is flung away. In this exchange, the planet's own orbit is slowed by an infinitesimal, utterly unmeasurable amount. But the spacecraft, in a kind of gravitational slingshot, is hurled outward at an enormous new velocity. It has gained this speed for free, without burning a single drop of extra fuel. This was the investigation put into action. The most famous examples are the Voyager probes, launched in 1977. They were designed to take advantage of a rare planetary alignment that happens only once every 176 years. Voyager 1 flew past Jupiter, its gravity bending the probe's path and flinging it towards Saturn. At Saturn, it did it again, using the ringed planet's momentum to accelerate it out of the solar system entirely. Voyager 2 went even further, conducting a grand tour of Jupiter, Saturn, Uranus, and Neptune, using each planet in turn as a gravitational slingshot to propel it to the next. These probes are, to this day, among the fastest objects humanity has ever built. Voyager 1 is now travelling at over 17 kilometers per second, moving so fast that it has officially left our solar system and entered the stillness of interstellar space. This speed was not the product of a giant engine. It was the product of a clever idea. The investigation had shown that speed in space doesn't always come from strength. Sometimes it comes from understanding the rhythm of celestial motion. But the gravity assist is an opportunity, not a constant. You must go where the planets are, and you must wait for their alignment. The investigation, therefore, had to find other ways to achieve speed, ways that were continuous and controllable. This led to a radically new kind of engine, one that traded the violence of the rocket for the persistence of a whisper. This was the investigation into ion propulsion. A chemical rocket works by throwing a huge amount of mass, burning fuel, out the back at a relatively low speed. An ion engine does the exact opposite. It works by taking a small amount of propellant, often an inert gas like xenon, and giving it an electric charge, stripping its atoms of electrons to create ions. Then, using powerful electric or magnetic fields, it accelerates these individual ions out of the engine at incredibly high speeds, sometimes over 30 kilometers per second. The thrust from this is minuscule. The force produced by an ion engine is often less than the weight of a single sheet of paper pressing on your hand. You could not use it to launch from Earth. It could not even overcome its own weight. But in the vacuum of space, where there is no friction, that tiny, gentle push never stops. This was the new investigation, trading power for patience. A chemical rocket roars for minutes. An ion drive hums, almost silently, for years. Over time, that relentless, whispering push accumulates. Day after day, week after week, that gentle acceleration adds up. The spacecraft moves faster and faster, reaching speeds that no chemical rocket, with its limited fuel supply, could ever hope to achieve. This idea, once a dream, became a reality. NASA's Deep Space One probe, launched in 1998, was the first to truly test this technology, using its ion engine to fly by an asteroid and a comet. But the masterpiece of this investigation was the Dawn mission. Launched in 2007, Dawn used its ion engines to do something previously unthinkable. It travelled to Vesta, one of the largest bodies in the asteroid belt, and entered orbit. After a year of study, it simply turned its engine back on and, slowly and gracefully, spiraled away, leaving Vesta's gravity to travel for another 2.5 years to the dwarf planet Ceres, where it entered orbit a second time. This was a spacecraft that could visit 2 separate worlds, a feat impossible for a chemical rocket, which would have burned all its fuel just to get to the first. Dawn's engines fired for nearly 5 years in total, but it used less than 500 kilograms of xenon fuel. It was the ultimate proof that in space, endurance is its own kind of power. The investigation, however, did not stop there. If a tiny, efficient engine was good, what about no engine at all? What if a spacecraft could move without carrying any propellant? This was the most elegant investigation of all. It was the pursuit of the solar sail. The idea is as simple as it is beautiful. Sunlight itself carries momentum. Light is made of particles called photons, and though they have no mass, they have energy and momentum. When a photon strikes a surface and reflects off it, it imparts a tiny, tiny push. On Earth, this pressure is immeasurable, lost in the noise of wind and gravity. But in the vacuum of space, it is a constant, free, and infinite source of propulsion. The investigation was to build a sail, a vast, thin, perfectly reflective sheet that could catch this light. The sail would need to be enormous, perhaps the size of a boxing ring or a football field, but also incredibly thin and light, made of materials only a few micrometers thick. Once unfolded in space, the constant stream of photons from the sun would push against it. The acceleration would be almost imperceptibly small, less than a millimeter per second squared. But like the ion drive, it would be relentless. As long as the sun shines, the sail would accelerate, moving faster and faster, all without a single drop of fuel. This, too, moved from theory to reality. In 2010, the Japanese Ikairos mission successfully deployed a sail and demonstrated controlled flight, its trajectory bending measurably under the gentle pressure of sunlight. The Planetary Society's light sail missions later proved the same principle in Earth orbit. The investigation had revealed a new way to move, a form of cosmic sailing, a way to align with the flow of photons that already fill the universe. This is where our investigation stands. We have turned our curiosity into action. We have learned to collaborate with gravity, to build engines of patience, and to sail on the light of our own star. But even these profound, elegant solutions are still, by the standards of the cosmos, slow. They have opened up the solar system, but the stars remain impossibly far. The investigation, therefore, must go deeper. If we are to ever truly reach for the stars, we must investigate new, more powerful sources of energy, beyond chemistry, beyond even light. We must look into the heart of the atom itself. The investigation was not just a theoretical exercise. It was not a dream confined to blackboards or laboratories. The pursuit of new ways to move, of collaborating with gravity, and building engines of patience led to real machines. And these machines, in turn, began to send back real data. They sent back clues and fragments, whispers from the void that would, piece by piece, build a new map of the possible. This is the story of those records, of the swiftest machines humanity has ever built, and the quiet, persistent data they continue to send home. Our story of verifiable records begins in 1977, with the launch of two of the most enduring travelers we have ever created, Voyager 1 and Voyager 2. These spacecraft, each about the size of a small car, were designed to study the outer planets, Jupiter and Saturn, and their moons. But their true genius lay in their timing. They were launched to take advantage of a rare planetary alignment, a gravitational pathway that opens only once every 176 years. This was the ultimate test of the gravity assist theory. As Voyager 1 passed close to Jupiter, it fell toward the planet's immense gravity well, gaining speed. It then swung away, stealing a tiny, imperceptible fraction of the planet's orbital energy, and was flung outward towards Saturn. It repeated the process at Saturn, accelerating again, this time on a trajectory that would fling it out of the solar system entirely. The data from this maneuver was staggering. The final record for Voyager 1's speed is over 17 kilometers per second, or 61,000 kilometers per hour, relative to the Sun. This is a speed that is difficult to hold in the mind. It is fast enough to travel from New York to Los Angeles in less than 4 minutes. And yet, the testimony of its journey is one of profound patience. Even at this astonishing pace, the scale of the universe dwarfs it. It took 35 years for Voyager 1 to reach the edge of the Sun's influence, a region known as the heliopause. In 2012, it crossed that boundary and entered interstellar space, the first human-made object ever to do so. It is there now, more than 24 billion kilometers away, still moving, still coasting on the momentum it gathered decades ago. The clues and fragments it sends back are the faintest we have ever received. Its signals, travelling at the speed of light, now take more than 22 hours to reach Earth. When we receive its data, we are, quite literally, listening to the past. Its twin, Voyager 2, followed a different path, conducting a grand tour of all 4 giant planets: Jupiter, Saturn, Uranus, and Neptune, the only spacecraft ever to do so. Each encounter added to its velocity, pushing it, too, into the eternal drift. The data from the Voyagers was a revelation. It showed that speed in space doesn't always come from strength, but from a deep understanding of the rhythms of celestial motion. The next great record holder was a machine designed for a destination that once seemed unreachable: Pluto. The New Horizons mission, launched in 2006, set a new record for the fastest object ever to leave Earth. At its launch, it departed our planet at nearly 58,000 kilometers per hour. Its journey across the solar system took 9.5 years. For much of that time, it hibernated, a silent traveler in the deep cold, waking only periodically to check its systems before resuming its quiet flight. When it finally arrived at Pluto in 2015, it sent back the data that transformed a distant, icy dot into a world. For the first time, we saw mountains of ice, vast frozen plains, and the faint, shimmering hint of an atmosphere. These images were the clues, the reward for a decade of patient, high-speed travel. And then, its primary mission complete, New Horizons continued on, coasting on its launch day inertia, deeper into the Kuiper Belt, where it sent back data from an even more distant world, Arakoth. These probes, however, were all outward bound, gaining speed as they escaped the Sun. The greatest speeds, the current record holder, were achieved by a machine that did the exact opposite. The Parker Solar Probe, launched in 2018, was designed to do what was once thought impossible: to touch the Sun. To do this, it had to perform a counterintuitive maneuver. Instead of accelerating away from the Sun, it needed to slow down its orbit, allowing it to fall inward toward the Sun's immense gravity. To shed this speed, it used repeated gravity assists from Venus, dipping close to the planet to slightly slow itself down relative to the Sun. And as it falls closer to the Sun, gravity takes over. The probe accelerates to velocities that are almost beyond comprehension. By 2024, Parker had reached speeds of nearly 700,000 kilometers per hour, or about 430,000 miles per hour, relative to the Sun. This is, by a huge margin, the fastest human-made object in history. It is fast enough to travel from the Earth to the Moon in less than an hour. To survive this speed and proximity, it carries a revolutionary carbon composite heat shield, a thick protective layer that withstands temperatures over 1300 degrees Celsius, while keeping the instruments operating in its shadow at a comfortable room temperature. This is the verifiable evidence. We have the records. Parker Solar Probe is the fastest relative to the Sun. The Helios probes of the 1970s, also sundivers, reached over 250,000 kilometers per hour. The Juno spacecraft, in its long, looping orbits of Jupiter, is periodically accelerated by the gas giant's gravity to over 265,000 kilometers per hour. But what is the nature of this data? What are these clues and fragments in their truest form? The most important piece of data is that speed in space is not a sensation. It is a calculation. It depends entirely on what you compare it to. Parker is the fastest relative to the Sun, but Voyager 1 is the fastest on a one-way trip out of the system. An astronaut on the space station is moving at 5 miles per second relative to the ground, but relative to their floating coffee cup, they are perfectly still. The data we receive is not a reading from a speedometer. It is a faint, fragile, and delayed echo. We find these clues in the faint signals gathered by the giant dishes of the Deep Space Network. We track these probes, billions of kilometers away, by measuring the tiny, subtle Doppler shifts in their radio frequencies. Just as the sound of a siren changes pitch as it moves toward or away from you, the pitch, or frequency, of a radio signal shifts with velocity. By measuring that shift with exquisite precision, we can calculate, not feel, how fast our explorer is moving. The fragments are the data packets that ride on that signal. The temperature of the Sun's corona from Parker, the magnetic field readings from Voyager, the digital images from New Horizons. Each of these is a testament, a piece of knowledge returned to us on a whisper of radio waves, delayed by minutes or, in Voyager's case, by nearly a full day. These machines themselves are a form of testimony. They don't experience their own speed. If you were aboard Voyager, you would feel no motion at all. No vibration, no wind, no sound. You would simply float in a quiet room, surrounded by an endless, silent dark. The speed of these machines is not a measure of violence or energy, but a measure of endurance over silence. They are able to maintain their record-breaking speeds for a simple reason. In the vacuum, there is nothing to slow them down. Their motion is a gift from that first, brief, fiery launch, a gift that will last for eons. This data, these records, have transformed our understanding. They are extensions of human perception. The cameras that captured Pluto's ice mountains, the sensors that felt the particles of the solar wind, all of them are our senses, extended across the solar system, travelling at speeds we cannot. They transform speed into knowledge, and these records are already guiding the next investigation. We now have the data to design missions that will go even faster. Concepts for solar sails that are not just pushed by the sun, but by powerful, Earth-based lasers are on the drawing board. Projects like Breakthrough Starshot imagine these light sails could propel tiny gram-scale probes to a fraction of the speed of light, reaching nearby stars within decades instead of millennia. The data, clues, and fragments we have gathered so far are our most honest reflection. They are humanity's will to move, turned into metal and circuitry. They show that even when we cannot follow in person, we can send our curiosity ahead. The records set by Voyager and Parker are not just numbers for a book. They are proof that our motion can last, and that our understanding can continue to grow, even in the deepest, quietest, and fastest parts of the void. The data from our fastest machines, the clues and fragments sent back by the Voyagers and the Parker solar probe, have given us an answer. But it is a difficult one. The answer is that we are, by the standards of the cosmos, almost perfectly still. Our most astonishing speeds, our greatest technological triumphs, are, in the face of interstellar distance, a glacial crawl. The nearest star beyond our Sun, Proxima Centauri, is over 4 light-years away. This is a distance that shatters our intuition. At the speed of our fastest probe, a machine like Voyager 1, the journey would take more than 70,000 years. 70,000 years. That is longer than all of recorded human history. from the first cave paintings to the very screen you are watching now. This single, crushing fact is the source of the great intellectual drama of our time. It is the problem that forces our minds to divide. The chemical rocket got us to the moon, but it cannot take us to the stars. The elegant, patient engines, the ion drives and solar sails can explore our solar system with beautiful efficiency, but they, too, are far too slow for an interstellar crossing. The wall of distance and the wall of time seems absolute, and so humanity's brightest minds have split. They have divided into different schools of thought, different philosophies on how to solve this impossible problem. These are the conflicting theories that define the future of human motion. The first theory, the first school of thought, is one of patience. This is the theory of the generation ship. This group of thinkers looks at the 70,000-year number and does not see a barrier. They see a time scale. This theory accepts the slowness. It proposes that if a journey takes longer than a single human life, then the journey itself must become life. This theory suggests that we must build vessels that are not ships, but worlds. Ecosystems in miniature. Vast arcs carrying thousands of people, not as travellers, but as residents. These ships would be so large and self-sustaining that they would become their own homes. They would carry artificial gravity, vast gardens for agriculture, systems to recycle every drop of water and every atom of air, indefinitely. The people who left Earth on such a ship would know they would never see it arrive. Their children and their children's children would be born in motion, living and dying in the quiet, endless cruise between the stars. For them, home would not be a planet. It would be a continuity of care, a shared inheritance of metal and light, a vessel carrying the memory of a world they would never see. Their progress would be measured not in speed, but in continuity. This is the theory of endurance. It is beautiful, poetic, and, to many, profoundly sad. And so, another school of thought arises in direct opposition. This is the theory of power. This group of thinkers refuses to accept the time scale. They believe that patience is not the answer, that a more powerful, more violent, and more revolutionary engine is. This theory says we must stop thinking about chemistry, which is limited by the energy in its bonds, and start thinking about the nucleus. This is where the minds truly divide, on the question of how to unleash this power. The first, and most audacious, of these theories came from a secret project in the 1950s and 60s. It was called Project Orion. The concept was bold to the point of absurdity. It proposed to propel a massive spacecraft by ejecting small nuclear bombs behind it and riding the shock waves. Each explosion would push against a massive, cushioned metal plate at the back of the ship. This theory was not fantasy. The engineering was considered feasible. A ship, powered by nuclear pulses, could, in theory, reach speeds of 10% the speed of light, reaching the nearest stars in decades. But the political reality was impossible. Detonating hundreds of nuclear devices, even in space, was an idea the world could not, and would not, accept. The power theory had to become more refined. It had to move from the brute force of fission, the splitting of atoms, to the elegant, powerful, and clean energy of fusion. This is the great dream. Nuclear fusion is the engine of the sun itself. Inside every star, gravity squeezes hydrogen atoms so tightly that they merge, forming helium and releasing vast amounts of energy in the process. A fusion engine would be a star in a bottle. The energy it could release is millions of times greater than any chemical fuel. A ship powered by a fusion drive could, in theory, accelerate continuously. It could reach Mars in weeks, the outer planets in months, and the nearest stars within a single human lifetime. This theory is not just a dream. It has a blueprint. In the 1970s, a group of scientists and engineers developed Project Daedalus. It was a detailed plan for an uncrewed interstellar probe designed to reach Barnard's star 6 light-years away within 50 years. The Daedalus engine would not be a steady burning star. It would use high-powered lasers or electron beams to ignite tiny pellets of fusion fuel, creating a rapid-fire series of micro-explosions, each one adding thrust, accelerating the ship for years until it reached 12% of the speed of light. This is the central, conflicting theory to patience. It is the theory of sub-power. But even this dream has its own divide. What if fusion is not enough? Beyond fusion lies the most powerful and most mysterious energy source in the universe: antimatter. When a particle of matter meets its twin, antimatter, they do not burn, they annihilate. They convert 100% of their mass into pure energy, a perfect expression of Einstein's E equals Mach 2. A single gram of antimatter, reacting with a gram of matter, would release as much energy as a nuclear bomb. An antimatter engine is the most efficient propulsion system that physics allows, but the conflict here is immediate and absolute. Antimatter does not exist in nature. We must make it, particle by particle, in giant accelerators. The process is so inefficient that producing a single gram would take millions of years and unimaginable expense. And even if we could make it, how would we store it? It cannot touch normal matter or it would explode. It must be held in traps of pure magnetic fields, suspended in a perfect vacuum. This theory seems impossible, but a third hybrid theory has emerged. What if we used antimatter not as the fuel, but as the spark plug? This theory suggests using tiny, microscopic amounts of antimatter to catalyze or ignite a much larger fusion reaction. This would combine the efficiency of antimatter with the power of fusion. And then there is the final theory, the one where minds divide completely, leaving engineering behind and entering the realm of pure theoretical physics. This is the theory of the loophole. This school of thought looks at the problem and says, what if we are asking the wrong question? What if the problem is not that we need a better engine? What if the problem is that we are trying to move through space at all? This theory suggests that we should not try to break the speed of light, which is an absolute law of the universe. Instead, we should find a way to go around it. This is the intellectual drama of theoretical concepts, like wormholes or the Alcubierre warp drive. The Alcubierre drive, proposed in 1994, is a solution that works perfectly on paper. It does not propel a ship through space. Instead, it propels space itself. The theory imagines a bubble of space-time. In front of the bubble, space-time itself would be contracted. Behind the bubble, it would be expanded. The ship inside the bubble would be perfectly stationary. It would feel no acceleration, no motion at all. It would simply be carried along, like a surfer on a wave, as the fabric of reality itself moves. This wave, this warp bubble, could theoretically travel faster than light without ever locally breaking the law. But here, the conflict is absolute. To create this effect, to bend space-time in this way, the equations require a form of matter that has negative energy, or negative mass. This is a substance that, as far as we know, does not exist. It is a mathematical possibility, but a physical impossibility. It works on paper, but the paper is the only place it works. This is the great divide. The human minds investigating this problem are spread across this landscape of theories. The pragmatists, who believe in the slow, patient path of generation ships. The engineers, who believe in the tangible, achievable power of nuclear fusion. And the dreamers, who believe that the ultimate answer lies not in power, but in a loophole in the very laws of physics. In our journey so far, our minds have divided. We have seen the great schools of thought that seek to solve the problem of interstellar distance. We have the dream of patience, the vast, slow-moving generation ships, arcs that carry humanity's future across millennia, accepting the timescale of the cosmos. And we have the dream of power, the roar of fusion engines, the perfect, terrifying efficiency of antimatter, all seeking to shorten the journey, to bend the timescale of the universe to the length of a human life. But beneath all of these theories, beneath the blueprints for engines and the dreams of voyagers, lies a deeper mystery. It is a mystery that is not an engineering problem, but a feature of the universe itself. It is a single, fundamental and unyielding barrier. It is the wall against which all our theories of speed, no matter how powerful or patient, must eventually collide. This is the deeper, hidden truth of our story. It is the discovery that the universe has a speed limit. That limit is the speed of light. It is a number that seems arbitrary at first. Just under 300,000 kilometers per second, or about 186,000 miles per second. But this is not just a record. It is not a technological barrier that we can one day hope to break with a better engine, just as we broke the sound barrier. This is the fastest possible pace at which reality itself allows change to travel. It is the speed of causality. It is the speed of information. It is a boundary woven into the very fabric of existence, and it is absolute. For any object with mass, a ship, a person, a single atom reaching this speed is not just difficult, it is impossible. Why? This is where the mystery escalates, where the simple question of how fast opens up a profound new understanding of the universe. The answer lies in the theories of Albert Einstein, published in 1905. His theory of special relativity begins with one simple, radical idea. The speed of light is constant, no matter who measures it or how fast they are moving. This idea shatters our intuition. If you are in a car moving at 50 miles per hour and you turn on your headlights, you might think the light from your car is moving at the speed of light plus 50 miles per hour. It is not. It is moving at the speed of light. Exactly. Because the universe insists on this one. Perfect. Unchanging. Constant. Everything else in the universe must bend to accommodate it. Time, distance, and even mass are not fixed. They are elastic. They are relative. And this is where we find the wall. As an object with mass accelerates, as it moves faster and faster, its energy increases, but so does its effective mass. It becomes harder and harder to push. As you approach the speed of light, this resistance becomes exponential. The energy required to gain that next increment of speed grows and grows, until, at the very moment you would touch the speed of light, the energy required becomes infinite. Infinity is not a metaphor here. It is a literal, mathematical fact. There is not enough energy in the entire known universe to accelerate a single human being to the speed of light. The universe itself, in its fundamental geometry, resists that final step. We have seen this in our most powerful machines. In particle accelerators like CERN's Large Hadron Collider, we push tiny protons to 99.999999% of the speed of light. At that speed, their mass increases more than 7,000 times. We can push them, spending enormous amounts of energy, to get infinitesimally closer. But they never, ever, reach the limit. This is the hidden truth. The speed of light is not a goal to be reached. It is a boundary that can only be approached. Only massless particles, like the photons of light themselves, can travel at this speed, and they must. They cannot travel any slower. But this discovery, this absolute limit, opens up an even deeper, more emotional mystery. If mass grows with speed, what happens to time? Einstein showed that time and space are not separate. They are a single, interwoven fabric, space-time. And this fabric is flexible. When you move through space at high velocity, your motion through time slows down. Speed, it turns out, carries a weight. And that weight presses not on your body, but on the flow of time itself. This is not a theory we can choose to believe or not believe. It is a law of nature, tested and confirmed so many times that it has become one of the most reliable truths in physics. We see its proof every single day. The Global Positioning System, the GPS in your phone, relies on a network of satellites orbiting the Earth at about 14,000 kilometers per hour. Because of that motion, their onboard atomic clocks tick just a tiny bit slower than the clocks on the ground. The difference is minuscule, a few microseconds per day, but if our computers did not constantly correct for this relativistic effect, the entire GPS system would fail within minutes. Every time you check a map, you are quietly relying on the fact that time is elastic. We see it in particles called muons. These particles are created high in Earth's atmosphere. They have such a short lifespan, measured in microseconds, that they should decay long before they ever reach the surface. And yet, we detect them on the ground in large numbers. The reason is time dilation. Because they are travelling at nearly the speed of light, their internal clocks run slow from our perspective. Time for them stretches just enough to let them complete the journey. This is the mystery. This is the something bigger. Speed does not just change your location, it changes your duration. For astronauts on the International Space Station, the effect is small. When astronaut Scott Kelly spent nearly a year in orbit, he returned to Earth about 5 milliseconds younger than his identical twin brother, Mark, who stayed on the ground. But the effect is real. Now, imagine a ship that could travel at a significant fraction of light speed, a ship powered by the fusion or antimatter engines of our dreams. At 99% the speed of light, time for those aboard would flow about 7 times slower than for those on Earth. A journey that, to the crew, feels like 5 years, would be 35 years for the world they left behind. This is the profound and deeply human mystery that our quest for speed has uncovered. It presents us with a heartbreaking paradox. The faster we go, the more we become separated, not just by space, but by time. A crew on an interstellar voyage would leave home young and could return, still young, to a world where everyone they ever knew has been gone for centuries. This is the emotional weight of the speed limit. And this leads to the final, deepest part of the mystery. Why does the universe protect this limit so fiercely? Why is causality, the link between cause and effect, tied to the speed of light? The answer is that the speed of light is the speed of now. It is the rate at which one part of the universe can communicate with another. When you look at the sun, you are not seeing it as it is. You are seeing it as it was 8 minutes ago, because that is how long it took its light to reach you. When you look at the nearest star, Proxima Centauri, you are seeing it as it was 4.2 years ago. When you look at the Andromeda Galaxy, a faint, fuzzy smudge in the night sky, you are seeing a memory from 2.5 million years ago. From a time before modern humans existed, the universe, as we see it, is a tapestry of the past. The speed limit is what holds this tapestry together. If you could travel faster than light, you could, in some frames of reference, arrive at a destination before you left. Cause and effect would unravel. You could, in theory, create a paradox that would destroy the very logic of history. The speed limit, then, is not a cage that confines us. It is the fundamental rule that keeps time itself from collapsing. It is the law that ensures the universe makes sense. This is the ultimate hidden truth. The universe is vast. And the journey to the stars seems impossibly long because this law, the law of light, is what defines that distance. The limit of our speed is not a technological problem. It is the language of the cosmos itself, the steady, constant rhythm that ensures all of existence moves in harmony. We have arrived at the final, and perhaps most profound, turning point in our journey. It is not a new engine. It is not a new destination or a new, impossible speed. It is a turning point in perception. It is the moment our investigation into motion leads us to the overwhelming, contradictory, and beautiful discovery that in space, the faster you go, the more the universe insists on stillness. It is the realization that the ultimate experience of speed is, in fact, indistinguishable from perfect, absolute rest. This is the great paradox. On Earth, our entire understanding of speed is built on sensation. Motion is a physical, tactile event. We feel it as a force, a vibration, a pressure. We feel the rush of wind against our skin, the rumble of the ground beneath our feet, the way the world blurs past our windows. Speed, for us, is a conversation with our environment. It is the sound of friction, the feeling of resistance, the noise of our own power. A car vibrates, a plane rumbles, a rocket, in its ascent, shakes the very air and ground for miles. But in space, all of this vanishes. The moment the engines cut off, the moment acceleration stops, the universe changes. The turning point is this transition, the thunder of launch, the crushing weight of G-forces, the violent vibration. It all disappears in an instant. It is replaced by a silence so total, so complete, that it feels like the end of motion itself. And yet, in that moment, the spacecraft is moving faster than it ever has, faster than any human had ever moved before. This is the strange, new reality. In the emptiness between stars, speed begins to lose its meaning. An astronaut in orbit is moving at 17,500 miles per hour. They will circle the entire planet in 90 minutes. But if they release a pen from their fingers, it does not fly backward. It floats, gently, weightlessly, beside them. The astronaut, the pen, and the cabin around them are all falling together in a perfect, shared motion. To the senses, there is no movement at all. There is only a profound, floating calm. This is not a deception. It is a fundamental law of physics. Our bodies do not and cannot sense velocity. We can only sense changes in velocity, acceleration, deceleration, or a change in direction. In the vacuum of space, once an object is in motion, it remains in motion, unchanged, infinite, and silent. There is no air to resist it, no friction to slow it down. This is Newton's first law, revealed in its purest, most perfect form. The astronauts who first experienced this were surprised. They reported sensations of stillness so profound that they sometimes lost track of which way their spacecraft was oriented. Only the sight of the Earth, gliding past the window, proved that they were moving at all. Motion became a matter of thought, of intellect, rather than a feeling. This turning point, this transition from feeling speed to calculating it, is even more profound in deep space. Far from Earth, on a journey to Mars or Jupiter, even the visual cues of motion vanish completely. There is no rising or setting of horizons. There are no clouds rushing past. The planets are distant points of light. The stars, which we use to measure our position, are so impossibly far away that they appear fixed. They do not blur. They do not streak. They are a static, frozen backdrop. Imagine you are aboard the Voyager 1 probe, our fastest interstellar traveller. You are moving at over 17 kilometers per second. You have been traveling for nearly half a century and have crossed more than 20 billion kilometers. And yet, if you were inside that tiny craft, you would feel nothing. You would simply exist in a quiet room, floating in the dark. The journey would be indistinguishable from standing still. This is the turning point. The realization that speed in the cosmos is not a property. It is a relationship. It is an abstraction. It exists only in mathematics and telemetry. Motion is relative. It only becomes visible when compared to something else. This is the great illusion. A spacecraft halfway between planets has no absolute speed. It is moving relative to the sun. It is moving relative to the galactic center. It is moving relative to the cosmic background radiation. Each of these is a different number. Each of these reference frames gives a different answer, and all of them are true. This realization turns back upon us. It forces us to confront the illusion of our own existence. We feel, at this very moment, that we are at rest. The ground feels solid, the air calm, the world steady. But this, too, is an illusion. We are living inside the very paradox we are trying to describe. Even in stillness, we are voyagers. The Earth is rotating at over 1,600 kilometers per hour. It is revolving around the Sun at nearly 30 kilometers per second, and the entire solar system is sweeping through the galaxy at 220 kilometers per second. We are hurtling through space at speeds no human technology can match. Yet we feel none of it. We feel stillness. Why? Because, like the astronaut in the capsule, everything is moving with us. The atmosphere, the oceans, the ground beneath us all share the same momentum. There is nothing to measure against, so we experience rest. The universe, it turns out, does not tell us we are moving. We have to figure it out. This is the great, humbling turning point. It teaches us that motion, one of the most fundamental aspects of existence, is something we can never feel directly in its truest form. We can only feel the changes. The push of acceleration, the resistance of friction. Once those vanish, motion becomes a silent, invisible constant. This realization is not a deception. It is a state of equilibrium. On the larger scales, the universe itself expands. Galaxies drift apart, carried on the stretching fabric of space-time. Yet from within our own galaxy, that expansion is imperceptible. The stars seem fixed. Even the cosmos, at its most dynamic, wears the mask of calm. There is a profound comfort in that symmetry. The illusion of stillness that surrounds us, whether on this planet or in a ship in deep space, is the same illusion that defines the universe. Motion is everywhere, but it hides itself behind balance. The faster something moves in a vacuum, the more constant, and therefore more still, it feels. This, then, is the new challenge for our future explorers. It is not just a technological challenge, it is a psychological one. To travel the cosmos, we must learn to be comfortable with this illusion. We must place our faith not in our senses, which will tell us we are motionless, but in the invisible, abstract, and unwavering truth of mathematics. The turning point is the acceptance that movement and stillness can exist together, indistinguishable, eternal. The quiet heart of speed is not a roar or a rush. It is the perfect, silent continuity of motion that never stops, that never demands attention, that simply is. We have arrived at the turning point. We have accepted the profound, almost spiritual contradiction that the fastest motion we can achieve, the silent, frictionless coast of orbit, is experienced by the human body as perfect stillness. This is not just a clever paradox, it is a fundamental truth of the universe. And this truth has consequences. It shows us that our entire journey into space is a story of exchange. It is a series of transformations where we trade one state of being for another, and every one of these exchanges comes with a price. The first, and most violent, consequence is the price of acceleration itself. To earn the right to that effortless, silent coast, we must first pay an enormous toll in energy, fire, and sheer, brutal force. We cannot enter that state of grace gently. We must be hurled into it. Every journey through space begins with fire. Not metaphorical fire, but the literal, controlled, thundering combustion of chemicals powerful enough to lift tons of metal and human life against the pull of an entire planet. This is the first cost, and it is written in the unforgiving language of physics. The tyranny of the rocket equation dictates this price. It tells us that to gain speed, we must throw mass, but to throw that mass, we must first lift it. This is why a rocket on the launch pad is a towering, delicate, and almost absurd compromise. It is a structure that is, by weight, almost entirely fuel. When the Saturn V stood on the pad, it was a tower of stored potential, weighing 3,000 tons. But less than 10% of that mass was the payload it was trying to carry. Everything else, all 90%, was propellant. It was a mountain of energy that existed only to disappear. The consequence of this equation is staggering. In the first 2.5 minutes of its flight, the Saturn V's first stage burned over 2,000 tons of fuel. That is 20 tons of propellant consumed every second. The energy released by that burn could power a city for hours, but in spaceflight, it was spent in less time than a song, just to cover the first few hundred kilometers of the climb. This is the price, and it is paid not just in fuel, but in stress. As the rocket ascends, it must fight its way through the atmosphere, a medium that resists it at every moment. There is a brief, terrifying window that engineers call max Q. This is the point where the combination of the rocket's accelerating velocity and the density of the air exerts the greatest possible mechanical load on the structure. The vehicle shakes, flexes, and groans under the tension. Every bolt, every seam, every weld is strained to its absolute limit. Every launch, no matter how routine, flirts with destruction for those few seconds. For the humans inside, the consequence is physical. The body is not just carried, it is crushed. During launch, astronauts experience acceleration forces of 3, 4, or more times Earth's gravity. This is not the push of a sports car. It is a weight, a giant, invisible hand pressing the body into the seat, making breathing heavy and movement impossible. This is the toll acceleration demands from human biology. And then, the second and most profound consequence occurs. The price is paid, the engines cut off. The consequence of this moment is silence. A silence so sudden and so absolute that it is, in itself, a shock. The thunder that shook their very bones is gone. The crushing weight that pinned them to their seats vanishes. And the body, which had been fighting against this immense force, is suddenly, impossibly, light. This is the great ripple effect. It is a physical, psychological, and philosophical transformation. The first ripple is physical. The human body is utterly confused. For your entire life, and for all of evolutionary history, your body has known one constant: down. The inner ear, the vestibular system, uses tiny, delicate crystals to sense the pull of gravity and tell your brain your orientation. In that instant of weightlessness, that system fails. The crystals float. The brain receives a stream of nonsensical data. There is no up, there is no down. Astronauts describe this initial disorientation as profound. The body doesn't just feel light, It feels lost. Blood, no longer pulled by gravity, rushes to the head, creating a feeling of pressure. The heart, no longer needing to pump as hard to fight gravity, shifts its position slightly in the chest. Even sleep feels strange, as the body no longer presses against a bed. This is the price of that perfect, silent coast. The body must learn to live in this new, impossible state. It must redefine its own sense of being. The next ripple effect is psychological. The consequence of this new state is a profound shift in control. On Earth, speed means freedom, but it also means connection. You press a pedal, you turn a wheel, you feel the feedback from the road or the air. You are in command. In space, this is no longer true. To go fast in space is to surrender control. Once the engines are silent, you are no longer flying. You are coasting. You are a projectile, a stone thrown into the void, coasting on pure, unfeeling momentum. There is no friction to slow you down, but there is also no air to push against. There is no steering, no stopping once the fuel is gone. Your path is now governed not by your will, but by the quiet, invisible laws of gravity and the momentum you earned in that first, fiery instant. Every maneuver now requires patience. To change your orbit, you cannot simply turn. You must fire a thruster, wait, and let the new trajectory slowly, gently take hold. The consequence of speed is that you must trade the immediacy of force for the long, slow, and humble art of patience. But the final consequence, the ultimate ripple effect of this entire endeavor, is one of perspective. This is the true price of discovery. When the astronauts, having paid the price of fire and endured the confusion of weightlessness, finally look out the window, they experience the transformation that changes them forever. They see the Earth, not as a map or a ground or a home, but as a planet. They see a small blue and white sphere, a delicate and luminous marble hanging in an absolute velvet blackness. They see the gentle curve of the horizon, the thin, glowing haze of the atmosphere, the swirling, silent patterns of clouds. They see a single, unified, and fragile world, with no borders visible, no sign of the divisions that define human life on the surface. This is the great exchange. This is the consequence. We pay an enormous, violent price in energy, in fire, in noise, and in the disorientation of our own bodies. And in return, we are given a gift of perfect silence, and in that silence, we are given a view that changes our definition of home forever. The roar of the rocket, the psychological price of disorientation, the surrender of control, all of it leads to this. A quiet moment of awe. The consequence of travelling so fast and so far is that you finally, for the first time, see where you began. You escape the cradle, not to abandon it, but to understand, as Konstantin Tsiolkovsky wrote, that the earth is our cradle, but one cannot remain in the cradle forever. The consequence of our journey into the void was not just a new set of technologies or a new list of records. It was not just the physical cost of acceleration or the biological confusion of weightlessness. The true, lasting, and most profound impact of our journey was a sound that echoed back to Earth and changed our collective history. It was the sound of a shutter clicking. It was the click of the camera that captured Earthrise, and later, the blue marble. This was the impact. This was the echo that travelled through time. In those first, fragile photographs, humanity saw itself. For the first time in our million-year history, we saw our home not as the ground, not as a map, but as a whole. We saw a small, delicate, and luminous sphere hanging in an infinite, silent blackness. We saw a world of impossible beauty, a marble of swirled white clouds, blue oceans, and brown continents, with no borders visible, no lines drawn by nations, no signs of the divisions that had defined us. The astronauts who took those pictures, the ones who had ridden the fire and the thunder to that quiet vantage point, all reported the same thing: a profound cognitive shift, a revelation. They realized in an instant that the true destination of their journey was not the moon. It was understanding Earth for the first time. This realization, this new perspective, was the echo that reshaped our world. The image of that single, fragile planet became the icon of a new awareness. It is no coincidence that the modern environmental movement began to gain powerful, global momentum in the years immediately following those photographs. We had finally seen, with our own eyes, that our world was a closed system, a single, shared, and finite cradle. That image alone did more to connect the individual to a collective sense of humanity than any speech or treaty ever could. We were all, quite visibly, in this together. But this echo changed more than just our culture. It changed the very nature of our quest. The race beyond the sky, which had begun as a fierce, geopolitical contest fueled by rivalry and fear, had, in a way, reached its conclusion. In achieving the moon, the race for pure symbolic speed had been won, and in the reflective silence that followed, the impact of that view from afar began to shift our priorities. The momentum of discovery continued, but its focus changed. The echo of Apollo was not a call to go faster, but to go smarter. The question was no longer, how fast can we reach space, but how long can we stay there? This was the birth of the next era of human spaceflight. The impact of the lunar missions gave us the era of endurance. The focus shifted from the sprint of the Saturn V to the routine, reusable flights of the space shuttle. The shuttle was not faster than the Apollo rockets, but it was more sustainable. It was designed to be a ferry, a vehicle that could carry crews and components into orbit again and again. And what was it building? The International Space Station, a place where, for over 2 decades, humans have lived continuously in that state of silent, high-speed motion. The ISS is, in itself, an echo. It is a symbol of how the race had changed. It was not built by one nation, but by a collaboration of many, including the 2 that had once been locked in that fierce race. The very instruments of rivalry had, in time, become the infrastructure of unity. This is the great echo through time. The quest for speed forced us to develop technologies that, once achieved, turned back to serve the Earth. The same rocket, technology that launched Sputnik as a political challenge, now launches satellites that connect our world. The high-speed orbits that were once a military frontier are now the backbone of our global civilization. Every time you check a map on your phone, you are using the echo of the space race. The GPS network is a constellation of satellites, each moving at thousands of kilometers per hour, each carrying an atomic clock that must be corrected for Einstein's theories of relativity. Every time you check the weather forecast, you are looking at data gathered by an orbital eye that sees the Earth as a single, interconnected system, just as the Apollo astronauts did. Every time you make an international phone call or stream a video from another continent, your signal is bouncing off a machine that is, at this very moment, falling around the Earth in a perfect, high-speed balance. The impact of our journey reshaped our world by connecting it. But the echo was not just technological, it was intellectual. The pursuit of these impossible speeds was, in a way, the grandest scientific experiment ever conducted. It was a test of our most fundamental understanding of the universe. For centuries, the laws of motion described by Isaac Newton were the foundation of our world. We used them to build bridges, to aim cannons, to understand the tides. The space race was the ultimate vindication of his ideas. The rockets, the staging, the fiery escape from gravity, it was all a testament to his laws of action and reaction, of gravity and mass. But this journey also forced us to confront the limits of Newton's world and enter the strange, elastic universe of Albert Einstein. To make our GPS satellites work, we had to accept his discovery that time itself slows down at high speeds. The pursuit of speed forced us to touch, for the first time, the weight of time. This is the echo that connects the individual to our collective history of thought. Every rocket that leaves the pad is not just a machine. It is a monument to thousands of years of human momentum. It is the physical embodiment of a story that began with ancient astronomers watching the planets, that was given language by Newton, that was refined by the quiet dreams of Tsiolkovsky, and that was finally proven by the courage of Gagarin and Armstrong. We, as a species, are the sum of all who dreamed before us. And that first great leap, that fiery race to the moon, was the moment all of that history, all of that curiosity, all of that restless human longing finally broke free of the cradle. The final impact is this. The race for speed ended by teaching us the value of stillness. The journey, which began with the loudest sound humanity could create, delivered us into the most profound silence. And in that silence, we saw ourselves. We saw our world, not as a place of division, but as a single, beautiful, and fragile island, adrift in a vast, quiet, and indifferent ocean. That image, that echo, is the most important piece of data we have ever brought back. It is the story that will live on, long after the records for speed have been broken, long after the footprints on the moon have been covered. It is the story that reminds us that we are all, right now, sharing the same invisible high-speed ride. We have spoken of the great machines, of the physics of escape, and of the vast, echoing impact our first journeys had on the history of the world. We have explored the cold mathematics of the rocket equation and the elegant, patient beauty of the gravity assist. But now, we must ground this immense cosmic scale in the one thing that gives it meaning. We must return to the beginning, to the why. This journey is not, at its heart, a story of metal, or fire, or numbers. It is, and has always been, a story about us. This is the human element. For all our technology, the quest for speed is not a modern invention. It is a fundamental, ancient, and deeply human longing. It is the need to see what lies beyond the next hill, the next ocean, the next horizon. We were runners before we were builders, sailors before we were pilots. This impulse is not just about exploration, it is about persistence. It is the quiet, stubborn, and magnificent refusal to accept that where we are is the only place we can ever be. This story, then, is about the dreamers. It is about the forgotten figures who built the foundations of our journey, not with steel, but with thought. Long before the first rocket ever left the ground, in the late 19th century, a quiet Russian schoolteacher, working in almost total isolation, was already dreaming of the stars. His name was Konstantin Tsiolkovsky. He was a philosopher of motion. He was the one who first penned the tyranny of the rocket equation, the one who first understood the necessity of liquid fuels and the elegant solution of staging. He laid the entire mathematical groundwork for our escape. But Tsiolkovsky was not just an engineer. He was a visionary. He understood the why. He understood the human element, the restless spirit that would one day need to leave. He is the one who gave us the phrase that would become the mantra for all explorers, the one that grounds our entire cosmic journey in human emotion. He wrote, "Earth is the cradle of humanity, but one cannot remain in the cradle forever." This single, beautiful idea is the very heart of the human element. It is the acknowledgement that growth means leaving the familiar, that to truly understand our home, we must one day see it from a distance. Tsiolkovsky, Newton, Einstein, these were the dreamers. They were the part of humanity that first moved, not with fire, but with imagination. But the human element is not just a dream, it is also a body, a fragile, biological machine, evolved for a very specific world of air and warmth, and, most importantly, of weight. The true, physical story of space travel is the story of this body and its profound, shocking encounter with an environment it was never meant to survive. This is where the story becomes visceral. When we speak of acceleration, it is not an abstract number. For the human element, it is a feeling. It is the feeling of launch. It is the violence of the price of admission. For the astronauts who climb into those tiny capsules, the journey begins with a controlled explosion. The pressure they feel is immense, a crushing force of 3 or 4 times Earth's gravity, pinning them into their seats. Their bodies, which are used to weighing a certain amount, suddenly weigh 4 times as much. Breathing becomes difficult. Movement is impossible. This is the human body's first startled response. It is being fought. It is enduring a trial, a physical test of its own limits. And then, in an instant, the engines cut off. The violence stops. The thunder ceases. And the human body is plunged into the second and most disorienting part of its journey. Absolute silence and perfect weightlessness. This is the deeper human element. It is the story of adaptation. The body is suddenly, profoundly confused. In your inner ear, tiny, delicate crystals, which have spent your entire life telling your brain which way is down by sensing gravity, are now useless. They float. The brain receives a stream of biological static. There is no up, there is no down. Astronauts describe this moment not as a freedom, but as a deep fundamental disorientation. The body must learn, in minutes, to abandon a sense that has defined its entire existence. It must create a new down, a new up, based only on what the eyes can see. This is the human element in its purest form. Not just enduring an environment, but learning it, adapting to it, and making it a new, temporary home. And it is here, in this new state of being, that the human element finds the great paradox. The astronauts are now moving at 17,500 miles per hour, but they feel nothing. They feel a stillness so perfect, so complete, that it is indistinguishable from rest. This is the human mind confronting a truth that the body cannot sense. The mind must trust the math. It must accept that this feeling of perfect calm is the feeling of moving faster than a bullet. This brings us to the final and most transformative part of the human element, the mind. What does this journey, this violence, this confusion, this paradox of stillness do to the human psyche? It delivers a revelation. It is an experience so profound that astronauts have called it awe. It is the moment they look out the window. It is the moment they see what Tsiolkovsky could only dream of. They see the Earth, a small blue and white sphere, glowing in the blackness. They see the gentle, perfect curve of the horizon. They see the entire planet, not as a map, but as a single, shared object. They see the thin, fragile, and luminous line of the atmosphere, a faint haze that separates their home from the absolute void. This is the moment that grounds the entire cosmic scale in human emotion. They are moving at unimaginable speeds, in an environment of impossible stillness, and in that moment, all their thoughts are of home. They see it, finally, as a whole, a single system, with no borders, no divisions, just clouds swirling over oceans. This is the human element. It is the dreamer, the philosopher, the quiet schoolteacher who first wrote the equations and gave us the why. It is the body, the fragile, biological passenger that endures the fire and learns to adapt to the quiet. And it is the mind, the consciousness that, in the end, looks back and discovers not a new world, but its own world for the very first time. We are a species defined by this longing, and this is why we will continue. This is why we dream of the future pilgrims, the ones who will take the next, even longer step, the ones who will board the generation ships and carry that human element, that fragile cargo of curiosity, memory, and hope into the stillness between the stars. They will be the ultimate expression of the human element, the willingness to carry the cradle with us on a journey that may never end. We have followed the human element on its grand journey. We have seen the dreamers, like Tsiolkovsky, who laid the path with mathematics. We have felt the physical trial of the astronauts, their bodies enduring the fire of launch and the profound confusion of weightlessness. And we have shared in the ultimate reward, the quiet, transformative awe of seeing our world from a distance. But now, our journey must face its greatest challenge. It is not an engineering problem, or a political one. It is not a skeptic we must convince. It is the universe itself. This is the opposition. It is the cold, indifferent, and absolute resistance of physics. It is the battle for truth, where our grandest ambitions collide with the fundamental laws of reality. And this opposition is not a wall that we can one day learn to climb. It is the very fabric of the cosmos, a rule that bends but cannot be broken. This opposition is the speed of light. For all our dreams of chasing the stars, of building fusion engines or harnessing antimatter, the universe has drawn a line. That line is 300,000 kilometers per second. It is not just the speed of light, it is the speed of causality. It is the fastest possible pace at which any information, any cause, can travel to its effect. It is the speed of now. And for any object with mass, a ship, a person, a single atom reaching this speed is not just difficult, it is impossible. This is the great, humbling battle for truth. Why? Why should there be a point beyond which speed is impossible? We are a species that has always broken barriers. We broke the sound barrier. Why not this one? The answer, discovered by Albert Einstein, is one of the most elegant and profound truths we have ever learned. It is the realization that the universe is built to protect this one single constant. And to protect it, everything else we thought was fixed, distance, mass, and even time itself must become elastic. This is the opposition. As an object with mass accelerates, as it moves faster and faster, its energy increases, but so too does its effective mass. It becomes heavier, it becomes harder to push. As you get closer to the speed of light, this resistance grows exponentially. The energy required to gain that next, tiny increment of speed becomes astronomical. To reach 90% of light speed, you need a vast amount of energy. To reach 99%, you need far more. To reach 99.9%, you need even more. The curve rises steeply, relentlessly, toward infinity. To accelerate a single human being to the exact speed of light would require an infinite amount of energy. There is not enough power in all the stars of our galaxy to pay that final price. This is not a theory we can choose to ignore. This resistance is real. We fight this battle for truth every day in our most advanced machines. In particle accelerators like CERN's Large Hadron Collider, we push tiny protons to 99.999999% of the speed of light. At that speed, their mass increases more than 7,000 times. We can spend a city's worth of power to push them infinitesimally closer, but they never, ever reach the limit. The universe resists. We see it in cosmic rays, high-energy particles born in distant supernovas. They are the fastest natural travelers we know. Yet even they, after traveling for millions of years, fall just short of light speed. The law is absolute. This, then, is the first great opposition. We cannot go faster than light. But the truth is more complex and more personal than that. The universe's resistance doesn't just block our speed, it changes us. This is the second, deeper opposition. The elasticity of time. Einstein revealed that space and time are not separate. They are a single, four-dimensional fabric, space-time. And we are all, always, moving through space-time at a fixed rate. That rate is the speed of light. If you are standing still in space, you are traveling through the time dimension at the maximum rate. But if you begin to move through the space dimensions, your motion through the time dimension must slow down to compensate. In simpler terms, the faster you go, the slower time passes for you, compared to someone standing still. Speed, it turns out, carries a weight, and that weight presses not on your body, but on the flow of time itself. This is not science fiction. This is the battle for truth that our engineers must fight every single day. The Global Positioning System, GPS, the network that guides your car and phone, is a constellation of satellites orbiting at thousands of kilometers per hour. Because of that speed, their onboard atomic clocks tick just a tiny bit slower than clocks on the ground. The difference is minuscule, a few microseconds per day, but it is real. If the GPS computers did not constantly correct for this time dilation, the entire system would become inaccurate by several kilometers within a single day. The system would fail. We fight this battle for truth just to know where we are. Nature demonstrates this truth all around us. High in the atmosphere, cosmic rays create particles called muons. These muons have an incredibly short lifespan. They should decay long before they can reach the surface of the Earth. And yet, our detectors on the ground record them in large numbers. The reason is time dilation. Because they are traveling at nearly the speed of light, their internal clocks run slow from our perspective. Time for them stretches just enough to allow them to complete the journey. This opposition has a human face. When astronaut Scott Kelly spent nearly a year aboard the International Space Station, he was traveling at over 7 kilometers per second. When he returned to Earth, he was about 5 milliseconds younger than his identical twin brother, Mark, who had stayed on the ground. It is a tiny, imperceptible gap, but it is a real one. It is the first time humanity has tangibly measured its own self-inflicted separation in time. And this is where the opposition becomes a source of profound, existential tension. What happens when the gap is no longer milliseconds but centuries? This is the true heartbreaking paradox for our power theories of fusion or antimatter. If we built a ship that could travel at 99% the speed of light, time for the crew would flow about 7 times slower than on Earth. A journey to a nearby star, which the crew might experience as taking 5 years, would be a 35-year journey for the world they left behind. If they travelled faster, at 99.99% of light speed, a 5-year journey for them could be a century for Earth. This is the opposition. This is the battle for truth. The faster we go, the more we become disconnected from the very home we are trying to represent. A crew of explorers could make the journey, arrive at a new star, and send a message home. But by the time that message, travelling at the speed of light, reached Earth, the civilization that sent them could be long gone. They would return, still young, to a world that knows them only as ancient history, as figures from a forgotten mythical past. This is the universe's quiet, powerful resistance. It does not forbid us from going to the stars, but it demands a choice. It asks, are you willing to pay the price? Are you willing to be cut off from time itself? This brings us to the final, philosophical truth of this opposition. The speed limit is not a cage. It is not a cosmic no. It is the very law that allows the universe to make sense. The speed of light is the speed of causality. It is the law that ensures before always comes before after. Every time you look at the sun, you are seeing it as it was 8 minutes ago. Every time you look at the Andromeda galaxy, you are seeing a memory from 2.5 million years ago. If you could travel faster than light, you could, in theory, outrun that light. You could arrive at a destination before you left. You could create a paradox, an effect without a cause, that would unravel the entire logical tapestry of history. The speed limit, this great, unyielding opposition, is what keeps time flowing in one coherent direction. It is the boundary that allows existence to have a now and a then. This is the true and most profound realism of our story. Our dreams of infinite speed must and will always be tempered by this beautiful, unchangeable, and necessary law. The battle for truth reveals that the limit is the truth, and it is a truth that ensures the universe, for all its vastness, remains a place of order, harmony, and consequence. We have reached the great opposition. We have stood before the unyielding wall of physics, the law that states that we, as creatures of mass, can never, ever touch the speed of light. We have learned that the universe is built to resist our ultimate ambitions, with an inertia that climbs toward infinity. And we have learned that the price for even approaching that limit is a profound and heartbreaking separation, not just of distance, but of time itself. It feels like a cage. It feels like the end of the story. The vastness of the cosmos, those 4 light years to the nearest star, and the 70,000 years it would take to cross them, all seem to tell us that we are, and will forever be, confined to our cradle. But here, in this place of profound limitation, a new awareness is born. This is the awakening. It is the moment that our human perception, forged on Earth, finally gives way to a deeper, cosmic wisdom. The awakening is the realization that we have been asking the wrong question. We have been obsessed with how fast, a question of numbers, of engines, of overcoming resistance. We have defined speed by the sensations of our world, by wind, by noise, by the blur of passing scenery. And the universe, in its infinite, quiet patience, whispers back the truth. The truth is that in space, none of those things exist. The awakening is the discovery that in the vacuum of space, in the frictionless, silent void, the state of moving very fast and the state of perfect stillness are not opposites. They are, in fact, the exact same, identical, indistinguishable experience. This is the great shift from knowledge to wisdom. On Earth, motion is a feeling. We feel the rumble of the train, the vibration of the car, the push of acceleration in our seats. We hear the roar of the jet, the thunder of the rocket. Our senses are constantly confirming our motion by registering the resistance of the world around us. But in space, there is no world to resist. There is no air, no medium to carry sound, no friction to overcome. The universe does not push back. This is why the human body, the machine evolved for sensation, is so profoundly confused. Our bodies, our nerves, our very brains are not built to sense velocity. They are built to sense acceleration, the change in velocity. This is the awakening. The most violent part of any space journey is the first few minutes. This is the moment of acceleration. It is the moment of noise, fire, and a crushing weight that pins the astronauts to their seats. And then, the engines cut off. The consequence is a transition so sudden, so total, that it is almost impossible to describe. The thunder stops, the vibration vanishes, The crushing weight disappears, and in its place is a silence so profound, a stillness so complete, that it feels like the universe has come to a stop. But it has not stopped. In that very instant, the astronauts are moving at 17,500 miles per hour. They are traveling 5 miles every second. They will circle the entire Earth in 90 minutes. And yet, they float. If they release a pen, it drifts calmly beside them. They are, by every human measure, moving at an unimaginable speed, yet their senses report only a perfect floating peace. This is the new awareness. Motion in the cosmos is not a feeling. It is a state of being. It is an intellectual understanding, a number on a screen, a piece of mathematics that your senses will actively deny. The astronauts who first experienced this were baffled. They reported a deep disorientation, a complete loss of up or down. Their inner ear, which relies on gravity, was useless. They had to learn to trust their eyes, to redefine their world, to accept that this feeling of absolute rest was the feeling of orbiting the Earth. This is the wisdom. We must unlearn our earthly intuition. Now, let us take this awakening and extend it far beyond the gentle fall of Earth orbit into the deep, dark, interstellar void. Let us imagine we are aboard the Voyager 1 probe. We are no longer in orbit. We have escaped the Sun. We are now travelling at over 17 kilometers per second relative to the Sun. We have been travelling for nearly half a century and have crossed more than 20 billion kilometers. We are in the true stillness between the stars. What would it feel like? The answer is nothing. It would feel like nothing at all. Here, in the deep, the illusion is even more perfect. There is no Earth gliding past the window to remind us of our motion. The planets are gone. The Sun itself has faded to just a bright star, indistinguishable from the others. And the stars themselves? They are so impossibly far away that even at this incredible speed, their positions would not change. They would not blur. They would not streak past, as our movies so often depict. They would hang, fixed, silent, and frozen, a static tapestry of light. We would be hurtling through the dark at 61,000 kilometers per hour, and we would be surrounded by a stillness so absolute, so profound, that we would have no way of knowing we were moving at all. This is the great law of inertia, Newton's first law, revealed in its purest form. An object in motion remains in motion, unchanged, infinite, and silent. This is the awakening. We have been chasing speed, defined by our earthly senses of noise and friction. But the universe has taught us that the true state of motion, the one that defines the cosmos, is silence. It is constancy. It is peace. This awakening reframes our entire struggle. The opposition of the speed of light no longer feels like a cage. It feels, instead, like a definition. And the slowness of our fastest probes no longer feels like a failure. It feels like the correct way to travel. The universe does not reward haste. It rewards endurance. This new awareness turns back on us and reveals the final, most intimate truth. This impossible state of high-speed stillness is not something alien. It is not something we must travel to the stars to find. We are in it right now. Even as you sit here, feeling perfectly at rest, you are a passenger on a planet that is spinning, orbiting, and sweeping through the galaxy at hundreds of kilometers per second. You, at this very moment, are hurtling through the cosmos at a speed that defies imagination. And you feel nothing. You feel only the stillness of your room. You feel this because, like the astronaut in the capsule, everything is moving with you. The air, the ground, the very chair you are in, all share the same perfect, constant high-speed motion. This is the wisdom. The stillness of deep space is not a foreign environment. It is the same stillness you are feeling right now. It is the natural, universal state of being. We have been in space all along. We have been travelers from the very beginning. The launch of a rocket is not, then, a journey from stillness to speed. That is our earthbound illusion. The launch is a journey from one speed to another. It is a brief, violent, and fiery change of course. This is the awakening. The quest for speed is not about overcoming the universe. It is about learning to be in harmony with it. It is about learning to trust the mathematics over our senses. It is about understanding that the true art of traveling the cosmos is not the art of the explosion, but the art of the long, patient, and silent coast. It is learning to be at peace with the profound, beautiful, and universal illusion of stillness. We have travelled so far, from the fire of the launch pad to the deep, philosophical calm of the void. We began with a question of how fast, a human question born of urgency, rivalry, and our restless need to conquer distance. We were met with the great opposition, the unyielding, absolute wall of light speed, a law that seems to cage us in our own small corner of the cosmos. And then, in that place of profound limitation, we found the awakening. We learned that our earthbound senses had deceived us. We discovered that the state of moving at thousands of miles per hour and the state of perfect, absolute stillness are, in the frictionless, silent vacuum, the exact same, indistinguishable experience. We realized that we are, at this very moment, already in that state, hurtling through the galaxy on a planet that feels, to us, perfectly still. This was the awakening. It was the shift from knowledge to wisdom. But now, we must face the final, deepest truth. This is the revelation. It is the moment we stop asking about our motion and start understanding the place we are moving through. The deepest truth, the one that redefines everything, is the nature of that stillness itself. The vast, dark, and silent expanse between the stars, the interstellar medium, is not a barrier. It is not an obstacle. And it is not, as we have always instinctively believed, empty. This is the revelation. The stillness between stars is not an absence of things. It is a presence. It is a place of profound, subtle, and unimaginable scale, and it is filled, not with the chaos of our world, but with something else. History. On Earth, we are surrounded by resistance. Our world is loud, chaotic, and dense. We live at the bottom of an ocean of air. A medium that carries sound, creates friction, and holds us down. Every motion we make is a fight against this medium. But the stillness between stars is the opposite. It is an environment of almost perfect equilibrium. Here, in this vast ocean, the silence is total. There is no air to carry sound. A supernova could detonate, an explosion of unimaginable power, and it would be perfectly, absolutely mute. Here, there is no friction to slow you down. A spacecraft, once it has paid its fiery price for acceleration, will coast on its momentum, unchanged, for eternity. This is the purity of motion, but this stillness, this vast, silent ocean, is not sterile. When we look closer, with instruments that see beyond our human senses, we find that it is, in fact, the largest, quietest museum in the universe. What is in this void? It is full of thin, ethereal gas, mostly hydrogen, spread so thin that there are only a few atoms per cubic centimetre. But this gas, stretched across light years, carries the memory of the first stars that ever burned. It is full of dust, not the dust of an attic, but the microscopic, precious ashes of supernovas. These are the tiny complex grains of carbon, silicates, and metals that were forged in the hearts of giant stars. Stars that lived and died billions of years ago. These particles, which will one day seed new solar systems, drift here for eons, untouched, a fine, cold and dark record of cosmic creation. It is full of radiation. It is pierced by the faint, ubiquitous and steady hum of the cosmic microwave background, the afterglow of the Big Bang itself, an echo of the universe's birth, still whispering in every direction. It is threaded with invisible, galactic magnetic fields, vast, slow currents that stretch between the stars, guiding the flow of these particles. This is the intellectual and emotional climax of our journey. The revelation is that the void is not a void. It is a place. It is the place where all the history of the cosmos is preserved, spread too thin to see, but present in every direction. And this revelation redefines our dream of interstellar travel. It means that a journey to another star is not a race across an empty track. It is a slow, patient, archaeological voyage through the history of time itself. This new, deeper truth also brings a new, deeper challenge. This is the paradox of the void. Because this medium is so still and so thin, it is a place of perfect, safe equilibrium. But because we intend to move through it fast, that same stillness becomes a profound danger. This is the hidden opposition, the one that waits for us after we have solved the problem of propulsion. Imagine our fusion ship, the one we dreamed of, accelerating to 10% of the speed of light. Now, imagine it moving through this empty space. That space is filled with tiny, microscopic grains of dust. To our ship, which is moving at an incredible velocity, these tiny, still particles are not dust. They are microscopic bullets. A single grain of dust, no larger than a grain of sand, striking a ship at that relative speed, would have the impact energy of a bomb. A collision would be catastrophic. This is the revelation. The faster we go, the more dangerous the stillness becomes. The faster we move, the more even the smallest thing matters. This means that any future interstellar craft will need shields. Not shields against alien weapons, as our fiction imagines, but shields against the very fabric of the cosmos. Shields against the dust and atoms that drift in the empty dark. But this challenge, this new opposition, is also what connects us. Those same atoms and dust particles are not just a hazard. They are the medium. They are the thin thread of matter that binds one star system to another. They are the sea between the islands. They are the raw material from which we were made, and the material to which we will one day return. The final revelation is one of time. Here, in this vast, quiet, stable place, time itself loses its urgency. In this stillness, a second, a century, and a million years flow with the same, even, uninterrupted ease. Motion here becomes perpetual. Look at our own messengers, the Voyager probes. They are in this stillness now. Their power is fading, and they will soon fall silent, but their motion will not. They will continue to drift, long after we are gone. In a million years, they may have crossed a fraction of the distance to another star. In a billion years, they may have passed through an entirely different region of the galaxy. They will outlive us. They will outlive the very memory of the world that built them. This is the deepest truth. It is the understanding that the universe does not reward haste. It rewards endurance. The concept of arrival becomes almost meaningless. Every destination is temporary. Every journey is perpetual. We started by asking, how fast can we go? The universe has answered by revealing the nature of the place we are going through. It is not a void. It is a vast, stable, and historical ocean, and it has taught us that the true art of travelling this ocean is not in the violence of the engine, but in the patience of the drift. The revelation is that we must learn to move not in opposition to the stillness, but in harmony with it. We must learn to see this emptiness not as a barrier, but as the quiet, steady, and eternal medium that holds everything together. We have come to a place of stillness. Our journey, which began with a question of fire and velocity, of how fast, has led us to the quietest, most profound place in human experience, the silent, weightless, and perfect calm of motion in the void. We have faced the great opposition, the absolute and unyielding wall of light speed, a law that protects the very fabric of time. And in that limitation, we have found an awakening, the realization that our earthbound senses are not equipped for the truth of the cosmos. Now, we must pause. This is the moment for that silence. This is the time to step back from the numbers, the engines, and the mathematics, and simply reflect on what it all means. What does this journey, this paradox of high-speed stillness, imply for our existence? The first reflection is on the nature of our own perception. We are a species born of resistance. We have evolved for a world defined by friction, by sound, and by the constant, unwavering pull of down. Our entire experience of motion is a story of effort. We hear the wind rushing past us. We feel the rumble of the ground. We hear the roar of our own power. To us, speed is noise. Speed is struggle. Speed is sensation. And the universe, in its infinite, quiet wisdom, has shown us that this is all a local illusion. The moment a rocket's engines cut off, all of that vanishes. The thunder stops. The crushing weight disappears, and the human body, for the first time, is plunged into an environment for which it has no reference. It is moving at 17,000 miles per hour, and it feels nothing. It feels a peace so profound, a stillness so absolute, that it redefines reality. This is the great, humbling reflection. Our senses, the very tools we trust to tell us the truth, are, in the face of the cosmos, unreliable. They are liars. The universe is not loud. It is not violent, except in its moments of creation. The natural state of motion, the state that governs the planets, the stars, and the galaxies, is a state of perfect, silent, and effortless continuity. This leads us to the second, deeper reflection. If this high-speed stillness is the true, natural state of the cosmos, then what are we? The astronaut in the capsule, floating weightlessly, is not experiencing something alien. They are, for the first time, experiencing the same state that we are all in at this very moment. This is the awe. We are not standing still. The ground beneath you, the room around you, the very air you are breathing, all of it is hurtling through the void at staggering speed. We are on a planet that is spinning, orbiting, and sweeping through the galaxy at hundreds of kilometers per second. We are, right now, the fastest travelers in the cosmos, and we feel nothing at all. The illusion of stillness, it turns out, is not limited to space. It is everywhere. We feel at rest only because, like the astronaut, everything in our immediate cabin, the atmosphere, the oceans, the ground shares the same perfect, constant motion. The astronaut, then, has not truly left. They have simply stepped outside the cradle, and in doing so, have seen the motion of the cradle itself. This reflection changes our entire relationship with the universe. We are not here, on Earth, with space being out there. We are in space. We are of space. We are, and have always been, voyagers. The launch of a rocket is not a journey from rest to motion. It is a journey from one motion to another. It is a brief, fiery, and human act of changing course. And what of the silence that defines this state? This is the third reflection, the one that introduces the deepest awe. The silence of space is not an absence. It is not emptiness. It is a presence. It is the sound of the universe moving in perfect, frictionless harmony. It is the sound of everything working. On Earth, noise is the sound of imperfection, of friction, of things colliding and breaking. In space, silence is the sound of equilibrium. It is the sound of planets in their orbits, of light crossing the void, of gravity holding everything in a steady, unending dance. The silence is not a void. It is the medium in which the cosmos happens. This changes our pursuit. We are a loud species. We have always equated power with noise. The rocket is our ultimate expression of this, but the universe whispers a different lesson. The greatest forces, gravity, light, time, the expansion of the cosmos itself, all work in absolute, profound silence. This is the awe. To travel in space is to learn to listen to this silence. It is to find peace in the fact that motion does not need to announce itself to be real. This leads us to the final, most human reflection. If the universe is this vast, this silent, and this bound by laws that forbid us from ever truly conquering it, then what is the point? Why do we try? This is the reflection on meaning. The journey into space, we have learned, is not a race for speed. It is a pilgrimage. It is a human act of longing, a search not for new lands, but for a new understanding of our place among them. The great opposition, the speed of light, is not a prison wall. It is, perhaps, the most important law of all. It is the law that makes meaning possible. It is the speed of causality. It is the rule that ensures before always comes before after. It is the law that keeps time flowing in one coherent direction, allowing a universe of cause and effect, of memory and history, to exist at all. If we could break this limit, the universe would dissolve into a chaos of paradoxes, a place where history has no meaning. The speed limit, then, is not an obstacle. It is the very rule that allows the story of the universe to be told. And our journey is our attempt to read that story. The awe we feel is the awe of perspective, the entire, violent, and expensive human effort to achieve speed, the race to the moon, all of it, had an unexpected, profound, and simple reward. It was a photograph. It was the Earthrise. It was the blue marble. In that moment of reflection, the journey's purpose was revealed. We did not go to the moon to conquer it. We went to the moon to see the Earth. We went to achieve the fastest speeds in human history, only to be given the ultimate gift of stillness, a single, fragile, and breathtakingly beautiful image of home. This is the ultimate meaning. We are a species that must leave, that must push against the limits, if only to earn the perspective to see where we began. Our journey into the void is, in the end, a journey back to ourselves. We are the part of the cosmos that has learned to look back, and in that reflection, in that profound, silent awe, we find our place. We are the voyagers, at rest in a universe of perfect, silent, and unending motion. Our reflection has brought us to a place of profound, high-speed stillness. We have found our own human place in a cosmos that is not loud, but quiet, not chaotic, but defined by an elegant, invisible balance. We have seen, through the eyes of our first explorers, our world as a single, fragile, and luminous whole. That image, that blue marble, is the great cultural legacy of our first age of speed. It is the story that echoed back and reshaped our consciousness. But there is another legacy. It is a legacy that is not an image in a history book. It is a physical, tangible, and ongoing story. It is the story of the machines themselves. It is the legacy of the quiet pilgrims we have sent into the dark, the ones who continue the journey in our name. This is the story of how our quest for speed lives on, not in memory, but in motion. When we speak of the fastest machines we have ever built, we are, in a very real sense, speaking of our ghosts. We are speaking of the probes like Pioneer, New Horizons, and, most famously, Voyager 1 and Voyager 2. These machines, built by human hands in the 1970s, are the enduring, physical proof of our restless curiosity. Their legacy began with the knowledge they gave us. They were our first true extensions of perception. They used the elegant, patient art of the gravity assist to swing from one giant planet to the next. They sent back the first close-up images of Jupiter's swirling, ancient storms. They revealed the staggering, intricate complexity of Saturn's rings. Voyager 2, on its grand tour, gave us our first and only close encounters with the pale blue-green worlds of Uranus and Neptune. They transformed distant, faint points of light into places, each with its own moons, its own weather, its own story. But their scientific mission, as profound as it was, is not their final legacy. Their true, enduring story began where their primary mission ended. After their last planetary encounters, they were flung outward, accelerated by the very planets they had studied, on trajectories that would carry them out of our solar system entirely. The engines that had given them their first push fell silent decades ago. They are now coasting. They are running on pure, silent, Newtonian momentum. And in the perfect, frictionless vacuum of space, there is nothing to slow them down. This is their legacy. They will never stop. Voyager 1, travelling at over 17 kilometers per second, crossed into interstellar space in 2012, the first human-made object to do so. It is now, and will remain, the farthest object we have ever sent from home. It is in the stillness between stars, a place where the sun's influence fades and the environment becomes the domain of distant, ancient starlight. The story of these machines lives on, in this very moment, in the form of a whisper. They are still transmitting. Their power, drawn from the slow decay of radioactive plutonium, is fading. But even now, across more than 24 billion kilometers of silence, Voyager 1 is still sending back data. The signals are unimaginably faint, a thread of information so weak it can only be heard by the largest radio telescopes on Earth. And this is where the legacy becomes almost poetic. Those signals, travelling at the speed of light, now take more than 22 hours to reach us. When we listen to Voyager, we are not hearing the now. We are hearing the past. We are listening to an echo from a machine that is already a full day farther away than the message it sent. That time lag, that 22-hour gap, is a tangible, human measure of the distance our ambition has created. This, too, is part of the story that endures, the fact that we are still listening. On Earth, teams of engineers and scientists still patiently gather these faint signals, still decoding the whispers from a machine that was launched before many of them were born. This is the legacy of human endurance, of our ability to sustain attention, to keep caring about what we've set in motion. But soon, within the next few years, their power will fade completely. The faint, whispering signal will cease, and then their final and greatest legacy will begin. They will become silent. They will become our first true artifacts. They will drift, unpowered and unhearing, for eons. They will outlive us. They will outlive our cities, our nations, and perhaps our species. They will continue to coast in that perfect, high-speed stillness through the interstellar dark. They are, in a very real sense, our first-generation ships, carrying not our bodies, but our memory. This is the most intentional part of their legacy. Aboard both Voyager probes is a copy of the Golden Record. It is a time capsule, a message in a bottle cast into the cosmic ocean. It is a single, gold-plated disc, engraved with the sounds and images of Earth, a greeting intended for any civilization that might, in the far, distant future, find it. This record is the story we chose to tell about ourselves. It contains greetings in 55 languages, the sounds of wind and rain, of whales and heartbeats, and music from all corners of our world. It is our legacy, deliberately crafted. It is a statement of intent, a whisper into the void that says, simply, "We were here. This is what we were like. We were a species of sound and science and wonder." The speed of these probes, which we worked so hard to achieve, is what gives this legacy its meaning. That speed is what carries this message, this small piece of our soul, into the vast, unending silence. The legacy also lives on in the probes that followed. The New Horizons spacecraft, which gave us our first breathtaking look at Pluto, is also on an escape trajectory. It, too, is now coasting into the dark, a silent testament to the next generation of our curiosity. The story of our quest for speed, therefore, has not ended. It endures. It endures in the scientific knowledge that reshaped our textbooks. It endures in the global, satellite-connected culture that those rockets made possible. It endures in the Earthrise photograph that still, to this day, has the power to inspire awe and humility. But most of all, it endures as a physical fact. It lives on in the cold, silent, and unstoppable motion of 4 small, human-made machines, drifting farther from home with every passing second. They are the swiftest machines we have ever built. They are our fastest messengers. And they are, perhaps, the most enduring legacy we will ever have. They are the quiet, physical proof that a species born in a cradle of gravity once learned to dream, to build, and to move. Our journey began with a simple, almost mechanical question. How fast can we truly travel in space right now? It was a question born of our earthly experience, where speed is a sensation, a roar, a rush against resistance. We chased numbers, records, engines of fire and thunder, believing that progress meant conquering distance with sheer, overwhelming force. But the universe, in its quiet, patient way, has answered us with a profound and humbling echo. It has shown us that our greatest speeds are, by cosmic standards, almost indistinguishable from stillness. It has revealed an absolute, unyielding limit, the speed of light, a boundary woven into the very fabric of causality, and it has taught us, through the silent drift of our fastest machines, that in the frictionless void, the feeling of motion vanishes completely, leaving only a perfect, paradoxical calm. This is the lesson that echoes beyond time. It is the wisdom that weaves itself into humanity's ongoing, and perhaps unending, cosmic journey. The true story of our speed is not about breaking records. It is about understanding. It is about learning to move within the rules of the universe, not in defiance of them. The echo tells us that speed is not the destination. It is the medium. It is the force that carries us toward everything we have yet to know. And the way we use that medium is evolving. Our first, fiery steps were born of necessity and rivalry. We built rockets of immense power because we had to fight our way out of a deep gravity well. That initial violent acceleration was the price of admission. But once we paid that price, once we earned our place in the quiet coast of orbit, the nature of our journey began to change. The echo of Apollo was not just the image of a fragile Earth. It was the realization that brute force alone could not take us much farther. The tyranny of the rocket equation remained. Chemistry had reached its practical limit. To continue our journey, we had to learn a new language. We had to learn the language of patience. This is the echo that resonates in our current exploration. Our most ambitious journeys now are not defined by the roar of launch, but by the quiet hum of endurance. Look at the missions powered by ion propulsion. Machines like Dawn, which visited 2 worlds in the asteroid belt, achieved their incredible feats not through explosive bursts, but through years of gentle, continuous acceleration. Their engines whispered, using electricity to push tiny amounts of mass at incredibly high speeds, trading intensity for an almost infinite endurance. This is the echo. Progress in space is shifting from the sprint to the marathon. Look at the dream of solar, sails, machines that carry no fuel at all, propelled only by the gentle, constant pressure of sunlight itself. Their acceleration is almost imperceptible, yet it never stops. They are learning to move in harmony with the universe's own energy, aligning themselves with the flow of photons that already fill the void. This is the echo. We are learning to collaborate with the cosmos, not just conquer it. Even our dreams of future, revolutionary engines, the fusion drives, the antimatter whispers carry this same echo. Yes, they promise speeds far beyond what chemistry allows, speeds that could shrink the solar system to weeks and months, and perhaps make the nearest stars reachable within a human lifetime. But even these engines are, at their heart, engines of patience. A fusion engine like the one imagined for Project Daedalus would accelerate for years, continuously, building velocity bit by bit. It is not the brief, violent roar of the Saturn V. It is a steady, controlled burn, a star held carefully in a magnetic bottle, its power released not in an instant, but over the course of a generation. This is the echo that travels beyond time. Our relationship with speed is maturing. We are moving from the impatience of youth to the endurance of adulthood. We are learning that the universe rewards consistency over violence. This shift changes the very meaning of fast enough. On Earth, fast enough means arriving sooner. It means beating the clock, shrinking the distance between departure and arrival. But in space, where distances stretch to light years, and the only true constant is the speed limit of light itself, fast enough becomes something else entirely. It becomes less about when you arrive, and more about if the journey itself is sustainable. Can the ship endure? Can the systems function? Can life, whether biological or artificial, persist across the immense, silent timescale of the voyage? This is the echo that shapes our future. Fast enough is no longer just a number. It is a measure of continuity. It is the speed that allows the journey to continue, unbroken, across generations. The generation ship is the ultimate expression of this echo. It is a vessel designed not for speed, but for permanence. It accepts the vastness of the timescale. It becomes a world in motion, its inhabitants measuring their lives not against the memory of a distant Earth, but against the steady internal rhythm of their own, moving civilization. For them, fast enough will mean the speed that allows their ecosystem to remain stable, their society to remain coherent, their purpose to remain intact across centuries of silence. This echo resonates back to us, here, now. It reminds us that we are already on such a journey. Our planet Earth is a generation ship. We are hurtling through the cosmos at incredible speed, carrying our own fragile ecosystem, our own history, our own future, on a voyage with no clear destination, only the imperative to continue. The silence of space is not out there. It is here. The laws of motion and time that will govern those future pilgrims are governing us now. The echo beyond time is the realization of our own inherent participation in this cosmic motion. We are not separate from the story of speed. We are the story, and this understanding changes the nature of our ambition. The question is no longer just how fast can we go? It becomes how far can life go? How far can consciousness, curiosity, and memory be carried into the future? The answer, the universe seems to whisper, is limited not by engines, but by endurance. It is limited by our willingness to sustain the journey, to pass the torch from one generation to the next, to find meaning not just in arrival, but in the quiet, steady, and unending act of moving. The echo beyond time is the legacy of the voyagers, still drifting, still whispering. It is the promise of fusion, still burning in our laboratories and in our imaginations. It is the quiet hope carried in the mathematics of warp drives, even if they remain impossible. It is, most profoundly, the stillness you feel right now, the silence in this room, the sense of perfect rest. This feeling, this illusion, is the echo. It is the universe reminding you that you are already moving at the only speed that truly matters. The speed of continuity, the speed of existence itself, unfolding patiently, second by second, across the vast, silent, and beautiful expanse of time. And so, our long journey through the landscape of speed arrives, quite naturally, at stillness. We began with a simple question, a human question rooted in our earthly senses. How fast can we truly travel in space right now? We sought a number, a record, a measure of our progress against the vast dark canvas of the cosmos. But the universe, in its quiet and profound way, has offered us something far more enduring than a number. It has offered us a reflection. It has led us through the fire and thunder of our own ambition, the race to escape, the power of rockets, the sheer, violent force required to leave our cradle. It showed us the limits of that fire, the tyranny of an equation that binds mass to fuel, and the vast, humbling distances that make even our greatest chemical engines seem small. Then, it guided us toward a quieter path. A path of patience, of elegance, of collaboration. We learned to borrow momentum from the planets themselves, turning gravity from an adversary into an ally with the graceful art of the gravity assist. We dreamed of engines that whisper instead of roar, ion drives pushing gently, continuously, for years, trading power for an almost infinite endurance. We imagined sails of light, catching the sun's own breath, moving without fuel, without sound, propelled only by the steady, silent pressure of photons. We even dared to look deeper into the heart of the atom, dreaming of fusion's clean, stellar fire, or the perfect, terrifying energy of antimatter, hoping to find a power that could finally shrink the void to the scale of a human life. But through all of this, beneath every engine, every calculation, every dream, the universe held its ground. It revealed its one, absolute law, the speed of light. Not a barrier to be broken, but the very rhythm of causality, the tempo that keeps time itself coherent, ensuring that before always comes before after. And in accepting this limit, we found the final, greatest awakening. We learned that our earthbound senses had misled us. We discovered the profound paradoxical truth that the state of moving at thousands of kilometers per second and the state of perfect, absolute stillness are, in the silent, frictionless void, the exact same, indistinguishable experience. This is where our journey ends. Not with a final speed, but with a return to the stars as they truly are. Silent, steady companions in a universe defined by motion, yet experienced as calm. As you rest here now, perhaps drifting towards sleep, let this final reflection settle around you like the quiet of space itself. The question, how fast can we travel, has dissolved. The answer is not a number, it is a state of being. You are, at this very moment, a traveller. The earth beneath you, which feels so solid, so still, is carrying you through the cosmos at speeds that dwarf any machine we have ever built. You are spinning, orbiting, and spiraling through the galaxy. A passenger on a world that has been in motion since its birth. And you feel nothing. You feel only the stillness of this moment, the quiet peace of your surroundings. This is not an illusion to be broken. It is the truth to be embraced. The stillness you feel is the same stillness that surrounds the Voyager probes as they drift through interstellar space. It is the same stillness that astronauts feel as they float in orbit, watching continents glide silently below. It is the natural, universal state of equilibrium, the peace that comes when motion meets no resistance. The journey into space, then, is not about escaping stillness. It is about finding it. It is about paying the fiery price of acceleration, enduring the confusion of weightlessness, and arriving, finally, in a place where motion and silence become one. The stillness between stars is not emptiness. It is the vast, quiet museum of the universe, filled with the faint whispers of creation, the dust of ancient supernovas, the thin gas holding the memory of first light, the echo of the Big Bang itself. To travel through it is to travel through history, through a silence that remembers everything. Our fastest machines, our silent pilgrims like Voyager, are now part of that silence. Their legacy is not just the records they set, but their persistence. They continue to move, not because of power, but because nothing stops them. They embody the lesson that the universe rewards endurance over haste, and perhaps that is the final answer to our question, how fast is fast enough? Maybe it is not about reaching a destination within a lifetime. Maybe it is about ensuring the journey can continue, unbroken, across lifetimes. Maybe it is the speed that allows life, consciousness, and memory to persist, carried gently through the dark. The universe does not rush. It unfolds at the pace of light, the pace of gravity, the pace of understanding. Our journey is simply to learn to move in tune with that rhythm, slowly, deliberately, and with a quiet reverence for the laws that hold everything steady. So, as you close your eyes, let go of the numbers, let go of the engines, let go of the race. Feel, instead, the stillness around you. Recognize it not as an absence of motion, but as the presence of perfect, balanced, and unending motion. You are already moving among the stars. You are already part of the great, silent, cosmic drift. The fastest speed you can travel, right now, is the speed of this moment, unfolding gently into the next. In that quiet continuity, in that shared journey through the stillness, perhaps we find the truest meaning of speed. Not how quickly we arrive, but how peacefully we continue. Not the roar, but the rhythm. Not the destination, but the drift. Welcome to the quiet side of motion. Welcome to the stillness that carries us all.